Microphone on. Hello, everyone. I hope you're ready for some 3D programming. Let's just have a look here. Okay, we've got about 7 people there, I think. So has anyone done some 3D stuff before? Has anyone not done any 3D programming before? And has anyone just started programming? So I'm kind of assuming everyone that follows along has a little bit of some sort of programming, but not necessarily any 3D graphics. And can you hear me okay? Okay, good. So my plan today was to do basically the video of the book. So just an introduction into how to get started with the first and most painful stuff with OpenGL programming, some of the basic concepts, nothing in depth. So just get something on the screen, do all the hard stuff, which is the setup, unfortunately. You should get something visual that you can start to play with, and that's the goal. So if we can do that before the hour is over, that'd be great. And then we could, in subsequent streams, if people want to, we could do something else more interesting or talk in more depth about things, or try another API. There's some interest in WebGL, so we could do that. But that's it. And I thought, okay, because OBS seems to work better for me on Windows, I'm going to do the intro on Windows, and because most people, students, have a Windows machine somewhere, a laptop or a lab machine or whatever, when you're learning, almost everyone tries to use um, Visual Studio when they start. It's not my favorite piece of software. When I'm on Windows, I don't use it very often, but I think that's most people will go through that. And actually, when you watch students starting OpenGL, this is the bit they get the most stuck on. Is not any complicated 3D mathematics or anything. It's getting Visual Studio to do what they want and start a project. Um, so I thought I'd do that, and I'd do that on stream. And then if there's any Q&A, probably I'll get stuck and I'll ask you questions. So I did a little dry run, and I think I got everything working. And I got all my swearing out beforehand. I thought that was wise. But I'll go through all of that and the basic ideas there. Okay, so just as a kind of a starter, I actually have a tutorial on my website. And if you want to go and do this kind of thing in your own time after the stream, you can do that. And I'll just see if I can drag this tab over. So this is my website. If you just Google Anton OpenGL, you will find it. And I have a list of tutorials there, and the top one is called Hello Triangle, and that's what we're going to go through now. And I also have a direct 3D starter there. So if you want to, after or before you've done this, try 2 different interfaces. So try Microsoft's interface as well. Same stuff. You'll notice a lot of similarities because it's talking to the same hardware, the same drivers, the same way, almost. It's just got a different eccentric interface to that. So you can produce the same kind of stuff, but this is more Windows specific tools, and it tells you how to get set up and all that kind of thing. So if you want a direct 3D starter, that one's there too. I've got a few parts, a few little articles here if you want to try something else that go into a little bit more depth for a few different interesting techniques, and a WebGL starter as well. Um, and I wrote a book of these things, which you could find on Amazon. It's called Anton's OpenGL 4 tutorials. Um, it's on itch.io as well. It's pretty cheap, but it's like 400 and something pages of these little exercise tutorials with troubleshooting in them as well. So if you get stuck, I've tried to anticipate basically the kind of things students in classes get stuck on. I've tried to do a Q&A at the end of every chapter there. So like that's available. It's a little out of date now. So you'll have to adapt it a little bit, but it should be okay. And yeah, anyway, let's carry on with this. Let's get rid of this tab. Okay. Okay. And so what we're going to do first is we're using OpenGL. I think we should target OpenGL. Specifically, the version we should target is 4.1. And so there are some really useful websites you're going to find helpful for doing that. Maybe I can make a new text file. I've made a folder of stuff here, which I'm going to use. I'm just going to put a text file in here. I'll come back to this other stuff shortly. Useful links. Okay. Oh no. It's doing that thing where it opens the file on the wrong screen and the window title is off the screen, so I can't click on it. I know there's a keyboard shortcut to grab it, but I don't know what it is. So, okay, that's painful. I'll open it with Visual Studio Code instead. How about that? Okay, so useful links. Well, my website, how small is that? Let's make that text bigger. Win shift arrows, that might work. Win shift. No, it doesn't seem to be doing anything. Oh, it did something. It did something. Is it there? I'm going to get it. I'm determined to get this now. Win shift. If I hit win shift down, it minimizes it, but I'm not sure how to move it to the other window. Okay, never mind. Let's do it in. Oh, there we go. Computers. Preferences. It's just dreadful interfaces these days. Dreadful. And I had to deal with a bit of that earlier when I did my dry run of Visual Studio. Okay, so my website, if you want to see my stuff, is antongerdeland.net/OpenGL, or just Google Anton OpenGL. So GL obviously stands for graphics library, and the first point we'll get to with OpenGL is not an open source library, which you might assume from the title. It is an open standard. So the specification of how you're supposed to use it, that's created by a group called the Kronos Group, which is a consortium of companies and graphics driver manufacturers and anyone who wants to contribute. There's a few academics in there, I think. Um, and they designed the specification for not just OpenGL, but Vulkan, another API, WebGL, various file interchange, file format standards, image standards, all sorts of stuff. OpenGL is one of the things. And they don't actually make the software. They just make the specification for how other people should implement it. And this is both kind of a blessing and a curse. It means that if you're using on Windows, the version of OpenGL that you will use, the implementation, because there is a little stub library driver thing to go with it, and that will be implemented by the company that makes your graphics driver. So I will be running NVIDIA implementation of OpenGL. If you've got an AMD device, you'll be using that one. If you're on Apple, regardless of which hardware you've got, it'll be running Apple's version of OpenGL. So unfortunately, they're not all identical. So you'll get slightly different bugs on all of them, but the interfaces should all be the same. And the reason I think we should use OpenGL 4.1 as a good starting point is I believe that is now the newest version that is likely to be supported on every platform, every newish platform. So that's a good starting point. If that doesn't work, you can try rolling back to an older one. I think it's unlikely you'll have to do that. If you want to try newer stuff later, you can bump that forward. So OpenGL 4.1, good starting point. My older writing tutorials and things suggest, I think, 3.2, which was the previous version that worked well on Apple. So that was a good starting point. I think this is now, and it may even be OpenGL 4.3 now on Apple that's supported. So in any case, I think this will work for almost everyone, and you can fiddle around if it doesn't. Other websites that are great resources, go and look up. The first thing you should do is look up from Kronos the OpenGL 4.1 quick reference card, and it looks like this, and you can print it out, and it's color coded, and it's just a list of all the functions in the interface. So this is a nice handy at a glance reference. The official specification is a gigantic unreadable, tries to be a tutorial in the first few pages, and then it rapidly falls away into a lacking context giant mega document worked on by a load of people. So you can go to that, but the use case for that is more like, oh, there's some specific funny little edge case I need to look up, and then I'll go to the the spec. But if you're learning stuff, that's not very useful. So this is a nice thing to get. It's only about 3 or 4 pages. It lists everything. You won't need all this stuff yet, but it's nice to have it there. If you want to see what similar alternative functions are to ones you are using, you can zip through, and then it has the shading language stuff at the end, which we'll come to later on a big index. So that's really nice, and printed out in color. Highly recommend that. So I'll put that on the list there too. So that's the quick reference card, really handy. Okay, and then there's another website you'll definitely want to know about. It's called docs.gl. And that is better and more easily searchable than the official websites that have lists of all the functions and a description of what they do, the API stuff. So it's called docs.gl. It is fantastical. And I'll just drag that over here so you can see. So the reason this is really cool is if you're looking up a function and that you want to use later, you can just type it in. And I think I was looking at recently, GL uniform is the name of the function. And there it is at the top, but it's also broken it down by version of OpenGL. And I wanted to use OpenGL 4.1's version of this. So I click on the last link there, GL4. But if I wanted to go and implement it in a different version for mobile, I'd use ES. For an older version of OpenGL, maybe I want GL2, but you can get specific information for your version, and it lists exactly what you. It's more readable. It lists exactly what you find in the official API HTML version of the API you'll find online from Kronos. However, if you scroll down, they often have little bits of example code and things at the end. Oh, and links to my website, which is pretty neat. Um, and they'll tell you in a nice little table, which versions of OpenGL support this. Oh, it didn't have an example for this one. Most of them do have a little bit of example code. So let's look at another one, maybe GL bind vertex array. This may be a good example. From OpenGL 4, let's look that up. And okay. I'm pretty sure they used to have little code examples, but maybe that's gone out of fashion. Okay, so perhaps that was too hard to maintain. I thought that was quite nice that it used to have those. So don't quote me on that anymore. Okay, so docs.gl, great reference. Okay, so what we're going to do is basically when you're drawing these days with 3D graphics, we want to use the GPU, which is hardware accelerated. It's very fast. Games use it for their graphics. And let's get rid of this. And I'll pull up my OBS window again. So if we're doing that, we have to use one of these driver type interfaces, a 3D graphics API. So I made another point there that OpenGL, it's not an open source library. Open specification. Okay. You don't need to go and download it though, so that's kind of nice. You don't need to go to some website and download this. If you've got your latest graphics drivers installed, it will install the latest version of the OpenGL stuff you need on your system already. So it'll already be there. Windows used to make their own implementation, and for some reason they haven't gotten rid of that, and it will hide in the Windows folder somewhere and use that by default unless you say, no, don't use this really old 1990s OpenGL. So we'll talk about how to avoid that, but that's a common pitfall. Yeah, APIs. So you've got OpenGL, Direct3D. Direct3D 11 is also a good starting point for starting. Vulkan I would avoid for learning. Metal is okay, a little bit more involved, but also reasonably good on Apple. And WebGL, of course, is really nice too. So that is a cut down version of OpenGL that's on the web, also really easy to get started with. We're going to do OpenGL. The nice thing is there is an implementation of OpenGL on just about every device. Direct3D, you're stuck on Windows. Metal, you're stuck on Apple. WebGL is really nice that it runs on everything, but you're not doing C or C++ programming for desktop software, for games. High performance games anyway, you're going to be doing online stuff, and it's really, really easy to share, which is great. I like WebGL a lot. A little bit different use case. Okay, so I think we can just start putting a program together. So we don't need to download OpenGL. Let's make a main.c. You know what? No, I was going to do this in Visual Studio, wasn't I? So let's start a new Visual Studio project. So if you're using Visual Studio 2019, and you do not need to use Visual Studio, I just thought that most people when they start tend to use this. So I'm going to go through this stuff. It's more, you absolutely can do all the same stuff on Linux or with GCC or with Visual Studio Code or on Xcode or from the command line. All of those are fine and probably a little easier to get started with. But I will do this because most people will do this. Create a new project. And we want to create a C++ project, and it's for Windows. And actually, I think we can make a console empty project. Okay, empty project. We don't want any starter stuff at all. And I'm going to put that in this folder somewhere. And I'm going to call it stream live starter code. You can call it whatever you want. So I did a console empty project. I want to have the console for using printf to debug stuff when I'm starting. Okay, so we get this interface, and I think I've adjusted all the fonts and stuff for the codes, so it should look a bit bigger. So if you go to your solution on the right-hand side, it may be on the left-hand side, and add a new item, you should be able to add a new file, a new source code file. I'm going to call it main.c. I do use C. OpenGL has a C interface. You can use C++. Most people use C++. You can also use other languages. You will find the same sort of starter information for Go, for Python, but then you will have to use bindings to those languages. There's plenty of packages available to help you get started. I shall do C though. If you're doing something different, that's actually a good idea to adapt what someone else does to your current style and then kind of make it your own. That's a really good idea in general when learning things. So definitely do that if you feel like it. Okay, so I'm gonna, as always, I'm gonna start with a blank file and do a little hello world just to make sure I've got my compiler set up properly. And then this is where I ran into my first tantrum earlier when I did my dry run. Does anyone have any questions about that kind of loose intro so far, actually? Okay. Okay. I think we've got 9 or 10 people there. No questions so far. Okay. So I'm going to do a hello world. Hopefully this will compile. However, the first thing I ran into was for some insane reason in 2020, Visual Studio still by default wants to build you 32-bit software. It's great that Windows still supports 32-bit software and you can run your old programs from the 90s. They will still run in some form, but I don't want to build software now that's 32-bit. There was a point a few years ago where that made sense because there were still a lot of laptops being built with more, less battery hungry 32-bit CPUs. That's not the case anymore. Everything's 64-bit. So the first thing you do is go up to this little drop down thing here beside where it says debug. It's perfectly okay to build debug builds and a good idea to do that when you're as a kind of a default, but change this to 64-bit build. It will drive you crazy later figuring out problems with libraries if you don't know which particular architecture you're building for. So we're building for 64-bit and we only want to build for 64-bit. So I'm going to put that on my little list here. Okay. One, switch. Oh, okay. We can say desktop console empty, and then 2, switch to x64 build. Can you read all of this stuff all right? Hello, alien. I think my font. I think my font should be okay about that big, right? This, I couldn't figure out how to get all the little side window things bigger, so hopefully that's not too much of a problem. Okay, so our first 64-bit Visual Studio program should now run and print in the console. That's why I wanted a console build. If you start building Windows desktop software, which you'll need to do for Direct3D, you will lose your little printf console, and it's really painful for development. So if you can, do console for your builds. Let's see if this builds and runs. Building ... There we go. Hello world up the top and a bunch of rubbish about the console there. So that looks fine. Okay, so that's our litmus test that I've at least got Visual Studio set up. Okay. Yes, you can. You can use Rustlang with OpenGL if you wish to. Yeah, so I actually think this is the hardest setup with Visual Studio, but I will do it. Yeah, all the other setups, I just have longer. They're saying that you can use Rustlang, and it's only about 50 lines of code to get everything up and running. Yes, this is the most painful way to start, but for one reason or another, this is what most students know when they're first coming to it, so they'll use this. However, they all get stuck on the linking library stuff, so I wanted to show you how to do that, even though it pains me greatly. Um, Okay, so what we want to do when you're creating any graphics these days on a modern operating system, it used to be a lot easier. If you go and look at Amiga graphics tutorials from the 90s, there's loads of these things. There's a whole retro community there. You'll see just how much easier it was to get started, and you can draw directly on top of your display. You don't need to do anything fancy at all. You can just start putting pixels down. You can't do that anymore, which is very unfortunate. These days, there's a lot of hoops to jump through to get started, and that's actually the hardest part. Mm, so what we need to do first is create a window. So if you want to draw anything these days, you need to open a window and draw into the window, designate an area you can draw into, and then draw into it. And you need to do this with all of the APIs. The first thing is creating a window. The problem with that is that on every operating system, there's a different little dance you have to do to open a window, include special systems headers, and then fill out all sorts of forms in structs and define funny little symbols. And if you want your program to go from, I'm running several different computers, and I like my software. I just want to concentrate on graphics. I don't care about this underlying Windows system stuff, and I want to be able to take my program and then compile it on Linux and run it there natively too. And you can do that. And if you really want to spend a lot of time, you can learn how to do all of these things yourself manually. Suggest you don't do that when you're starting. So some tutorials will say, go and learn about Win32 and then go and learn about Wiggle or WGL to hook up OpenGL to the window. Don't do that when you're starting. So what you want to do when you're starting is get rid of that and come back to it later for a rainy day and use a couple of libraries to help you. Okay, so what I suggest you do is go and get and download. There's two libraries that we'll need. And unfortunately, most students that I have been teaching, this is the hardest part because they haven't really dealt with libraries before at the point they start doing graphics. That's okay. It's something you need to learn and something you'll realize just how painful it is to use libraries with C and C++. So the first library you need to get, and this is the one I suggest you get, you do have lots of alternatives. There's a library called GLFW. And if you Google that or go to glfw.org, you will find the website, and it has a GitHub page. It's open source. And what it'll do is it will encapsulate or abstract that mess of starting a window, so that from your program's point of view, you don't care what operating system it is. You'll just say create a window, and it will do that. And it will also, all the other things operating systems do with Windows, like detect keyboard button presses and detect the mouse clicks and things a normal desktop program would use, it will also go and do those things for you and pipe them through to your program without you needing to know about Windows callbacks and all this kind of stuff. So that's really nice to have. It just separates that job out to a separate topic, which is exactly what we want. It will also do the hard work of tying your running copy of your graphics device instance, which you call a context. So a context is like a running session on the graphics device. Every program will have one context, but you can have several different programs all running on your graphics driver. So probably if you've got Discord open, it will be running some accelerated rendering. If you've got a web browser, it'll probably be doing some accelerated rendering. Each one of those will have a context that will talk to the graphics device. It may be OpenGL. As an interface, it may be Direct3D. It doesn't matter. That needs to tie to one window and only one window on the system. Okay, so GLFW will start your window for you. It will put it wherever you want, whatever size you want, put the little title on the top for you, and it will also start essentially OpenGL for you. It'll start a context when you ask it to and tie the context to the window. And what that means is when you go to draw stuff with OpenGL, it will draw into your window where you would expect it to be. So that is a very, very handy starter. And what I suggest you do is not actually clone the source code or download the source code directly, but if you go to the download page, because we're running a Windows build, there are pre-built binaries there. And remember that we set in Visual Studio, the first thing we did was set 64-bit build. And this is the number one place people get stuck, is mixing up which version of binaries for libraries that they're using. So we're doing 64-bit. We're only going to do 64-bit. Download the 64-bit version of the binaries. And you can download that into your, I put that in my same project folder there. So I have the zip file there. If you've downloaded the source code, it will look a bit different. I've unzipped that already. I just did this a couple of minutes ago. So this is the latest version. It looks like this inside, and it will contain different files for all the different versions of Visual Studio. So if you're running a different version, you'll find that there. If you're running GCC on Windows, you'll find a version for that there. So we're using Visual Studio 2019. Just make sure you've downloaded the correct architecture, and because the file names will not give that away. And then inside here, we've got 3 files. You have 2 options. You can either use, and that's what we'll do, is we will use option number 1, a DLL file. So that's a dynamic pre-built binary of the library with a little stub that we will give our program. We'll use that combination. So those 2 files, that may be a bit small for you there. Oh God, I don't know how I can zoom in. Never mind. We have glfw3.dll, and there's a little stub library called glfw3dll.lib. Your alternative is to use the static build that will build the whole thing into your program. I think you might have a little bit of a harder time setting that up. That's the middle one there, glfw3.lib. So there's 2 .libs. One's a little guy that's only 30 kilobytes. That goes with the DLL. We're going to use those 2. So I'm actually going to point back to this folder actually, but I'll copy the DLL file. We're going to need that later. And where did I put this? Stream started live code. Okay, so if you go to wherever you've saved your project, after we've built it, you'll see there are a number of folders that have popped up. One of them is called x64. And within this folder, we have debug, which is the build mode we've been building so far. Right, and in here we'll find our .exe, and you can run that. It won't do anything yet because it's just printing to the console. But that is the folder that we're going to paste in that DLL file because we are going to need that later. On Windows, when you run a program like this by clicking on it, it will first of all look in the same folder that the .exe is in for any DLL file it needs. So that is why I am copying that into the same folder. Okay, so that is the first little tricky bit. This will drive you insane if you are trying to figure this out from within Visual Studio. So this should be your first step. Build a hello world, find out wherever it spat out the .exe, make sure that you're building an x64, so 64-bit mode, and that you've downloaded the 64-bit version of the library. This is what most people get wrong, and it is infuriating to find out why, because you will not get sensible error messages. The difference between static and dynamic libraries is kind of a bigger topic, but when you're running your program, a dynamic library doesn't need to be built into your program. It's a separate file. Everything's built into there, and at runtime, you don't need to link this in to your program when you're doing compile and link. It's linked when you run your program. So if you move this file away, I will show you actually when we get it all set up. But if you don't have that in the same folder, you will notice that when you run your program, it'll go, hey, I'm looking for this file and I can't find it, which implies that it doesn't actually make that link. It doesn't link the symbols together until it runs. So that's what it means by dynamic linked library. It doesn't actually link to your program at all until you run your program. A static library will do all the linking as part of your build process and will build the whole thing into your exe file. So you no longer have this little dangly extra file. It's all built into this, and you'll have a much bigger .exe then. So that's a static library. The static library works almost identically to if you just compile one of your code files into an object file um, and build that into your program. So it's almost the same as that, as if you had another one of your source files, right? Um, so a dynamic library, yeah. So people got very excited about dynamic libraries in the 90s. Everything used to be static libraries. And the problem with static libraries was that if you're using someone else's third-party library and there's, for example, a security vulnerability in it, you can't actually just update your program without rebuilding everything. So the idea was that if some third-party person who you had a dependency on in some library, it would be really nice if that was built into a separate file, so you could just copy the new version onto the top, and you could let the user do that. You could do a little download. You didn't need to recompile anything. You didn't need to ship a new .exe. It would just work, right? That was the idea. But what actually happened, and people got super excited about it, and everything used DLLs, or on Linux they're called shared object libraries, .so, same thing, or on Mac they're called dylibs, .dylib. Um, so if you're on Windows and you haven't been coding much, it's important to know about all these different types of files. So make sure that you go into your view menu here somewhere and make sure you can see the file name extensions so you can see what you're dealing with. So what's a .exe, what's a .obj? That's a compiled source file, right? What's a .dll? So yeah, Windows has confused this with a .obj, which is another format, which is a 3D object. Yeah, so your dynamic link library, because you're doing that at runtime, it's probably going to be a little bit slower to get started. If you're shipping code, you can have so many problems with dynamic libraries. A thing emerged in the 90s called DLL Hell, and you can Google that and read about it. It was, for a long time, it was an absolute nightmare updating anything on Windows, especially if it used any 3D software. You had different versions of Visual Studio with different update patches that just would not run on anyone's computer, and you would need to go fishing around on the internet after a game you'd bought stopped working, and upload the correct package, and then it conflicted with something, and it was really horrible. So it solved some problems, but it introduced a whole lot more. And if you're trying to patch security vulnerabilities by letting the user install a new version of your library and having that by default look in the same folder that you're in. What that means is, so it'll look in your folder first, and then it will go looking in your system folders. Other operating systems do not allow this behavior by default, right? And the reason for that is that it introduces a huge security vulnerability. So if I had some Windows.dll or Direct3D whatever .dll in the Windows folder, what you can do and what people do, if they want to make a little hack, they can make their own program that pretends to be Direct3D's .dll file and stick it into, and they can sell this software to users and stick it in their game folder. So your game, when you run it, it will look in the same folder first, and it will find the illegitimate version of DirectX that someone has made that does DirectX. It'll pipe through to DirectX, but it also adds in their hacker software, right? So it'll do all sorts of extra stuff. So if you're playing a game, it can show you an X-ray view of where the baddies are in the world, and or whatever they want, or put a virus on your computer. So it's very, very high risk, problematic approach to libraries for software. So yeah, so it's a long-winded answer, but yeah, those are some interesting things to discuss, I guess. We're going to use a DLL because it's easier to get started. Um, I've had a little bit of trouble getting the .lib to work before, so I think this is the easiest way to get started. If you're on Linux, it's actually easier to install all this stuff. You can use your package manager, and probably the easiest way to get started is to just link against the shared object version of GLFW. Um, when you're distributing software to other people, because of this mess of DLL files or shared object files, it's easier to build the static libraries in. Then you don't have to worry about all these dangly little dependencies and making sure they're all in the right places and don't conflict with some system version. So generally, yeah, shipping software like a game or something, static builds are usually a bit safer, a bit easier to make sure they actually run on someone else's computer. Okay, sorry, that was a very long-winded departure from where I was going with that. So we want another library as well. So that will open a window for us. And I'm going to make a controversial recommendation, which I think is the easiest thing for beginners. And that's to grab this library here. And it's called GLEW. And this was for a long time the most popular library for a few purposes. The number one reason you want this library is, remember I told you there is a Microsoft version of OpenGL. If you try to just start OpenGL without using a little helper library, it will find that version, and you will be stuck with OpenGL version 1.1 and get really strange errors when you run stuff. So the first, I just see an ooh in the chat there, two of them. Okay, so the first job is you want a library that will fix that for you. So it will get the correct NVIDIA version or the correct AMD version for you. The other thing these libraries do, and the name kind of gives it away, Extension Wrangler, is if you want to use some extra stuff, some essentially add plugins for things, and you probably will need a few of these at some point, it will give you an interface for checking they exist and grabbing them so you can use the functionality for them. So I suggest you start with GLEW. There are alternatives to GLEW, and most people are horrified if I will bring this up. But from my experience, this is the easiest one to get started with. Everything else requires other steps of setup, which will further confuse people. And you got to install Python or go to some website and already know which functions you need. That's just too much. So this is a big, slow, clunky download, but it will just drop right into your project, and you don't need to worry about linking anything. So that is why I think this is the easiest way to get started. Okay, so GLFW, grab GLEW, and I'm going to make a note there. 3, download the 64-bit Windows binary download package for GLFW. Put into your projects folder and unzip. And then 4, download and we're not going to download a binary, we're going to download the source code for the GLEW GLEW library and put into your projects folder and unzip. So you will find on the download page here a zip file for the source code. You don't need to get the binaries, so we don't need to add in more than one library, just the one. And this one we can just drag in the source code, and that is fine. It is like a multi-megabyte piece of source code, and it has some annoying warnings and things. It's a bit clunky, but it will get us started, and that's all we need. If you want to upgrade to a more elegant solution, I would do that as a later step on some future exercise. But start with GLEW, start with GLFW. Okay, so in your projects folder now, where did I put this? Okay, let's go here and up one level. So I've got this is where I put my Visual Studio solution. Here's my text file. Here's the two things I downloaded. You should have a couple of zip files. Unzip them in here. I have GLFW. We already copied that .dll file. That's great. The GLEW I have here. What I'm going to do is go into the source for GLEW, and I'm actually going to drag this .c, glue.c, into my project. Right? That is going to avoid the pain of linking another library and compiling things and worrying about versions. So I think that is going to be an easier start. Let's try and compile that. It's going to give us heaps of warnings. We can shut some of them up. Okay, so it can't find the header file. So what we need to do is tell our project where to find the header directory. And this is where the pain begins with Visual Studio. So if you right click on your project, that is the second item down on your Solution Explorer, the one under the solution, not the solution. You'll get this menu. And this is the worst part of Visual Studio, in my opinion. So in here, we have this extremely eccentric list of stuff. There is a drop down there called C/C++. Under there, I don't even know where this thing is anymore. If you go to all options, you can type stuff in to search for it in any of those sub options within C++. So right at the top here, there's one called additional include directories. That is what we want. And if you click in the field beside that, there is a funny little drop-down arrow, which for some reason is a complete departure to all other Windows GUI stuff. And then if you click on that, there is a button called Edit, right? And that has a funny little new folder icon, which adds a new line to these funny little fields that will not fit things and they don't scroll very well. It's altogether a bit obscure. So what I'm going to do is go back to my folder and then go to GLEW. And it was looking for gl/glue.h. So I am not going to include the folder that contains gl.h directly, but I'm going to include this one. So if you go to your unzipped folder, you will have a bunch of subfolders in here, one of which is called include, and that's a more or less standard place to put header files. Inside that, you'll see you have glue.h and friends. We might need a few of these. But I'm not going to include this directory because it's actually trying to include GL/. So I'm going to go up one where I can see GL, right? And I'm going to click in my Explorer bar there and then just copy paste that whole line. So not including the GL bit at the end. And then I'm going to double click in here and then paste in and then hit enter. And then that should satisfy that requirement. So let's give that another whirl. The really tricky thing about these menus, and this is what drives me the most bananas, is that you have little drop downs here for debug and release and 64-bit and 32-bit, which means if you enter something in these menus, it only applies to the builds here. And if you have a mismatching version here where you're setting things in your panel to what you're actually trying to build, it won't pick this up. It will complain about the other thing. So it might save you some pain if we actually copy this, cut and paste this, and change this here to all platforms, because I don't want to do this again if I want to build in release mode. Do you want to save your changes? No. And then I will go in here, and hopefully there's nothing different in here. Okay, that's fine. I'm going to go in here and paste that over the top. Okay, and then hit apply. So that should now work for debug and release, I hope. No, I have to go all configurations as well. Okay, this is the most horrible user interface ever, but that is where people get really confused. Yes, I want all configurations and all platforms. So if I for some reason change it to 32-bit, I still want to use that include directory. If I for some reason change it to release mode, I still want to use that include directory. Yeah. It's very painful. So if you're not using Visual Studio, you don't have this problem. Um, but yeah, you get these two drop downs. So the left-hand side one is release or debug builds, and you want to be able to do both. At some point, debug's a nice default. You are going to want to switch to a release build eventually if you want to share this with your friends. Or if you want to check out the performance without the debug symbols built in. It should be a little bit faster, so you can get a better indication of your frame rate and that kind of thing when you're rendering. So you do want to switch between those. The reason that it breaks it down is because maybe you want to use a different version of a library for with debug symbols for debug builds. I don't think that's a big deal for us. We can use the same for everything. Okay, now I'm going to go right click and go rebuild, and it should find that now, but now spit out a bunch of warnings from the GLEW build, which it does. That's fine. So GLEW spits a bunch of warnings out. I'm going to just silence those because I don't need to know about all of those. But actually first there's some errors. So I'm going to only show the errors, and it's saying, hey, I can't find all these external symbols. So what we need to do, what is it complaining about specifically? Okay, WGL, so it's saying it can't find the Windows GL hookup stuff. What you need to do next is right click here, and we're going to add the OpenGL library into our library, our linking path. So not under C/C++, but under linker, we have yet another menu of stuff. And again, I'm not even going to bother clicking the submenus. I think it's on input actually. Yes. So we have, so I did bother. It wasn't that hard to find. We have this gigantic list of .lib files that are pulled into our program. Well, it's funny you should mention, you know how many tutorials are missing actually publishing, sharing it with people. Uh, yeah, I'm actually writing a book at the moment. We've nearly finished it, and we have a whole chapter with a whole lot of information about exactly that. It's called It Worked on My Computer is the name of the chapter. And It's about different things you need to consider for how to share your code. So not just runs on your computer in Visual Studio, but how do I give it to my friend so it runs on their computer? Or how do I, publish it for sale so people can download it and run it and pay me real money for it? So there's a bunch of tools for different platforms and different strategies. It's usually the libraries that are the problem. So we're doing a whole thing about that. So watch this space. Um, Microsoft actually has pretty good documentation for doing that. But I won't get into that now. Okay, so now I didn't mean to paste in there. So we have this list of .libs. What we need to do in there is add in OpenGL 32.lib. Now, for some crazy reason, even on 64-bit Windows, you'll see all of their system library files are called something something 32, Win32. They haven't changed the name of it, even though they've moved to 64-bit. So yes, yeah, we did cover Linux and Mac publishing. So Mac uses at bundles, um, and Linux you have a variety of strategies. Yeah, so we did do Linux and Mac. Yeah, yeah, I had to ship a game for with it was an OpenGL game for Linux and Mac as well as OpenGL as well for Windows. So we had to deal with all of those things. And it's a bit confusing when you first do it, but then you kind of get the hang of it. So I listed everything I could think of there. Yeah, sorry, I'm getting off topic. But OpenGL 32.lib, funny name, easy to add to our list of things though. So okay, put in your folders and unzip. Okay, what do we do next? Drag glue.c into your source tree. 6 is add glue's include subdirectory, not include /gl, to your project's project settings additional include paths list. Okay, and then 7, add OpenGL32.lib. And that is like your main OpenGL library. That is either NVIDIA or AMD or Windows. If you don't set the next steps up right, it'll find the Windows old 1992 one. OpenGL32.lib to your additional libraries path under project settings, linker settings, input under C, C++. Okay. Is that kind of clear so far? And I think that should work. Let's give that a whirl. Yeah, okay, so that works. It doesn't do anything yet, but it doesn't complain. Now let's silence a few of these excessive, or rebuild and silence a few of these excessive warnings. So you might see down the bottom there, it's complained about a million times about some clunky stuff in GLEW. I don't care about errors in GLEW. And it's come up with warning C4273 over and over and over again. It's just the one warning. And I'm just going to copy that part without the C, so 4273. And I'm going to go in project properties and shut this thing up. Now, I've already forgotten where this is. I think it's on C, C++, and Advanced. This is all the stuff I had to do a dry run for to find these funny little menus. Okay, and there is a field here called Disable Specific Warnings under C, C++ Advanced. And if you type that in, just 4273, don't put the C in front of it, that should shut that up. And if I go rebuild, no longer a problem. Good. Out of sight, out of mind. That's their problem. We're not going to worry about that. So I can add that to the list. Silence any GLEW compile warnings with project settings, C, C++, advanced, ignore warnings, and the error code without the C. Okay. So now we're ready to go. That is GLEW. We need to add in GLFW, but I think we could just start GLEW first. And it's going to give us some errors because it wants a context first before it does anything. But we can at least include GLEW now, and it shouldn't complain. So I'm going to put any third-party libraries, I like to put them above everything else in the include list, so that if they're missing a header, I'm not going to be including it by mistake. So I'm going to say include GLEW.h. No, it's not capitals. GLEW.h. And in fact, I think it was GL / whoa, what did they do there? GL/GLEW.h. Yeah, okay, that's perfect. And I can see it's already found that, so that should work. Yeah, that's perfect. Okay, now if I go back to the GLEW website and go to usage, it should give me a little example of how to start it. And there's a catch here, actually. There's a couple of catches. So ignoring all this stuff about glut, we're going to do that with GLFW shortly. Glut is an older helper library that's kind of it's out of date. Don't use glut. Don't use free glut. We're going to use GLFW instead. So anywhere you see GLUT, we're going to replace that with GLFW, or you can use SDL. Same deal. SDL has a whole lot more stuff we don't need though, so I think GLFW is a nice lean start. Okay, so it says what we need to call is GLEW init, and it returns an error code. And I'm just going to copy paste this stuff here. In fact, this whole bit, excluding the glut part. Okay, and the main reason again that we're doing this is so it finds the correct version of OpenGL to use on Windows. Okay, so it returns an error code. Now, you will, if you go and look up the definition of what it's checking for here, GLEW OK, and this is another thing people get stuck on, it will tell you it has the value of 0. So if you do this pattern that a lot of people will do and then go, why isn't it working? If you go if not GLEW init report error, that is going to fail even though it worked, because the correct code that nothing went wrong is a value of 0, which equates to false. So don't do this. Actually do something like this. If GLEW OK is not equal to GLEW init. So it doesn't work the same way as if this was returning true or false. And then we can report a little error here. I'll just delete this to shorten it down a bit. I'm going to return an error code and quit the program if I can't start GLEW. Oh, it does want it wants the error code there. Okay, so I'm going to cut this out. I'm going to say GLEnum, I think was the type it returned, or GLEWenum. Return equals. Let's just double check that. Oh, it is GLEnum. Okay. So it's using something OpenGL looking. Okay, that should work. Let's run it. I think it's going to say it won't start. There were build errors. Okay, what was the problem? Errors undefined. Oh, I called that variable ret for return. Okay, so missing GL version. That's because we haven't started a context. So in the example they gave, before calling GLEW init, they had already started glut to start OpenGL in a window in a context. So we will do that next. That looks okay so far. What was the compile error it gave us? It didn't give us a warning, did it? I think that's okay. I think that's all right. If I look in the header there, where this is, let's go go to definition. There was something up the top here. If I scroll all the way to the top and then search for GLEW static. No, not finding it. Search for static. I feel like there was a keyword there, GLEW static. Maybe I misremembered. Okay, turns out I did. I was sure there was. Okay. No, never mind. Oh, that wasn't the header file, so I need to go to declaration. So I saw something in the header file there that we might need to do. I don't know if it'll make any difference. So there is a hash defined there, GLEW static, and we aren't using a DLL. We're using the static version of the library, so we may as well help it out by telling it that we're doing a static build. So I'm just going to define that above where I include it, just in case it helps build things for some reason. I don't think it looks like it worked without it, but let's play on the side of caution there. Okay. Yeah, all right. So the next thing we want to do is actually start a window on the operating system and start an OpenGL context, tie them together, and then we'll start GLEW. And that should let us use the correct version of OpenGL, and we'll be able to check that all worked. So what we need to do next is this same kind of dance, but with the other library we downloaded. So where did we put this? Okay, so there's GLFW. I'm just going to use it from this folder. Now we're using Visual Studio 2019 and it's nicely labeled the subfolders there so we can find the bits we need. We already copied that DLL in. We are going to need this other .lib though, the glfw3 dll.lib, the little stub.lib that goes with our DLL file. We're going to feed it that. If you're running in Visual Studio, you don't need to explicitly add in these .libs. You can do a little pragma thing up here. Pragma, I think it's like pragma lib blah, 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 blah. But if you're running and then give it the name, and then you don't need to set it up in the menus if it can find it. But I'm not sure that's very helpful because if you're trying to do this on another operating system or even with GCC on Windows, that won't work. So let's do it the tedious way. So we need to add in the name of that glfw3 dll.lib into our same place. So under project properties and then linker and then inputs. So at the moment we've just got OpenGL32.lib we've added to the front. We need to add that one too. So it was called, I'm just going to copy paste this name here. It was called this. GLF. Don't use the other one. The other one's the static library and we're going to go the DLL route. Okay, so if I try and build that, it'll say it can't find it, I think. Yeah, can't find it. So I'm going to give it the path to that. So I'm going to go back to my Explorer and then copy paste this path where this guy lives. And okay, this is where it gets tricky. I'm going to go all options and just type in under the linker subdirectory there, type in additional. Okay, and then we've got additional library directories. That's what I'm looking for. I'm going to paste that in and then go apply. So I don't even know where all these things are. It might be under input. No, for some reason it's not the same place that you list all the files. There it is there under general, so additional library directories. So, and again, make sure you've got the correct platform, either all platforms are 64-bit and the correct stuff there. If you forget and some reason you've changed it in the meantime, it's going to drive you crazy. Okay, let's try this again, see if it finds it. Yes. Okay. So this is the most painful part of starting 3D graphics. They're all like this. Direct 3D has a whole lot of tedious setup as well. Different tedious setup. Oh, now we should be able to actually include things, but we might need to add the include directory for the other library there. So where are the header files? They're under include in GLFW. So let's include that. I want to go hash include glfw slash, so I won't get in here. I'll use the directory above this, okay? Just it's a nice little separator, and I think the libraries themselves might do that internally. So I'll keep that convention. So up here, remember we went gl /. So we have a little subdirectory there before the .h. So I'll stay with that convention. So once again, under project properties, C++, I've almost already forgotten. So general, additional include directories. We're going to go to this bizarre menu and add another one of these things in here and paste that in. And that should let us include the GLFW headers. So this is the insanity of Visual Studio. Now, there is a trick here. I think you want to include the GLEW header first, because that will include the correct OpenGL headers. There was something on the GLEW website about that. Let me just grab that. Where did I put it? GLEW. Okay. Yeah, so you will notice that in the GLEW documentation, they have said include glue.h first, and then afterwards include glut. We're not using glut. We're going to replace this with glfw, but that substitutes in there. We'll include that second. That's very important. That makes sure it pulls in the correct headers for you, and that's what we really want on Windows. So I'm going to say hash include, and then glfw is the name of that other subfolder. And then it's told us it's found at glfw3.h is the header we want. So this thing, I think, has hash define glfw, I think DLL. I have a note of that in my tutorial somewhere, I think. So I'm going to pull that over, where did I put this? Okay. So I've done this a little bit differently in my tutorial on the web, where I've used a DLL for GLEW as well, I think. But you'll notice that there's a little hash define helper there we can give to stop GLFW3 complaining when it builds and links. Just to give it a heads up to say, no, we're definitely using the DLL version, and put that above the GLFW3 header. So we're going to do the same thing there. And I was correct. Okay, so we are using the .dll, not the static.lib. On this one here is we are using the source code directly, not the DLL. Okay, this should give us all the tools we need to build this stuff. Let's try again. Rebuild. Okay, that's not complaining. So now I should be able to make glfw commands, and where's my little browser window? Okay, so there should be pretty good documentation on the glfw page for how to do this. So it's saying here, initialize the library, and then create a window, check if there's an error, then do this thing called glfw make context current. And what that's saying is get an OpenGL context and tie it to my window. So you'll see it actually gives your window variable that was returned with create window, it will give that to make context. So it's tying those two things together. So for OpenGL, one context, one window, they're tied together. And then you can start doing some OpenGL more fun stuff. So I'm actually just going to copy paste this and the whole lot, including that variable. And I'm going to put that before where we start GLEW, because GLEW is complaining that OpenGL wasn't started yet. So we'll do that first. Okay, let's compile that, see what happens. I'm going to do rebuild. It seemed to work, which is usually there's some sort of crazy linker errors, so I think we set it all up correctly for once. And it's running. It's not printing any cool stuff yet. And it looks like it's all working thus far, which is great. So that's the point you want to get to before you can actually start doing graphics, which is really painful, but maybe that helps to have that in tutorial form. I'm just going to check the chat messages. Quality options, and I don't know how to do that on a stream. If I'm honest, I'm not a very good experienced stream person. There may be some controls in Twitch, I don't know. There will be when I upload it to YouTube. You will be able to get a YouTube video, and perhaps buffering that up reduces the internet issues. I don't know. Otherwise, you can get a much more efficient version by I guess watching the low quality version and looking at a web page. So I have all this stuff on the web. Oh, okay. So quality options. Yeah, I don't know how all that stuff works. It's of course a business, so they want to encourage people to buy the pro version, I guess. That's certainly not within the realms of my experience to know the best way to do that. And I'm sorry about that. Okay, so there's some few interesting things here. So we are asking it to open a. Would you think multi-stream on Twitch? I've never tried YouTube. I could try YouTube next time. Yeah, I'll give that a go. I put that on my to-do list immediately. I don't know if YouTube is more tolerant to connection throttling or whatever. Yeah, I'll give it a go. I presume you can do both at once, but yeah, I'm just on a basic computer here. I don't know if you need a special setup or anything. Yeah, so creating a window, we give it a bunch of parameters here, and 640-480 sounds like a resolution. That's telling it what size you want the window to be. And these are like a humble request. It won't necessarily give you what you want if it doesn't fit. So you can try your best, and we can maybe make a bigger one. So maybe we'll go 1024. It can be any size you want. 768 perhaps, and give it a title. Hello chat. And then the other parameters there, GLFW has great documentation, so you can go and flick through. What it'll do there is let you choose which monitor you want it to be on, and null says use my default monitor, use my current main monitor, primary monitor. And what does the last command do? Windows share, I'm not actually sure. So that should be fine. There is a command to clean up and close the window properly. You'll see it's used here if there was an error starting. We should put that at the end where we close the program, just in case there's some residual window config that won't go away. GLFW terminate. I don't know what it's complaining about there. Let's just try and build that and see what happens. Did I? No, I didn't make a mistake. I don't know. I think it's a false error message. Okay, so there are some other things we want to do. So at this point, after we've done these things, we can make calls to the OpenGL stuff here. And you'll notice we got a few different types of function call here. We've got functions starting with lowercase glfw, equals glfw functions. Just be clear when you're looking at these things, which one's which. We have functions called glew dot dot dot, and those are GLEW functions. And then we're going to have shortly functions with gl dot 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 without the EW or FL, and those are OpenGL functions. Okay, and we're going to use some of them now. Okay, is everyone okay with that so far? So basically we're setting up a couple of helper libraries to remove some of the even more painful and tedious setup from us and get started straight away. Okay, so you can find these on your quick reference card or on docs.gl. I'll see where I put that. I think I've got it here. Okay, so there is a function called GL version, I believe. Is that right? It won't let me search. GL version. I think it's called version. No. Is it device? Let's see. What does the quick reference card have for us? And I actually have this on my webpage somewhere in my tutorial. Oh, okay. Sorry. It's get string. What I want to do is find out after I've started which version of OpenGL is running. And where did I put that? I've got too many browser tabs. I now have far too many browser tabs. Okay, so GL get string. And that will give us a string saying which, alternatively, depending on what parameters we give it, it will tell us which version of OpenGL is started in the context and what graphics device it thinks it's using. So if you're on a laptop, you want to print this out somewhere just to make sure it's using your hardware accelerated driver. Some laptops have two. They have a little built-in Intel thing, and if everything's going really slowly, maybe it's found the wrong um, hardware. So it's nice to print that out. So there's a function called glGetString, and we can see it returns a GLU byte. And OpenGL has all these type defs. That's just going to be a character. So that's going to give us a pointer to a string, essentially. They're just type def. If you look at your headers, they're usually type def to the basic C types. And the experts will tell you it does not matter. But if you ask very pedantic people on the internet, on Stack Overflow, or whatever, they will tell you, no, it's super important because on some systems the sizes might be subtly different. Maybe if you're on a mobile device, that's true. I don't know, but most of the time you can assume they're interchangeable with the basic C types. So this is just going to give you a string you could print with printf. And that was the design intention, as far as I'm aware. So these are the things you can give it. Vendor, renderer, version, and shading language version. You can try printing all of these things if you want to. What we want first, perhaps, let's see. Let's go with version. That's what we want. Find out which version of OpenGL is running. So let's see here. Let's try that. GL get string. GL version, I think, was the name of that thing. Okay. And I think we can just say char star version string. I think that'll work. Um, did I get that right? Whoops. Yeah, it's GL version. That should work. I don't know what it's confused about some layout thing somewhere. So if I just go printf the OpenGL version running is, and then %s for string, it should print that. So that is a nice little tester that something is working. Yeah, okay, so it said the version that's running, we haven't asked it to run a particular version. It's running 4.6. So it's on my system with NVIDIA. It's told us it's found the NVIDIA implementation of OpenGL. So look out for that. If it says Microsoft there, you're in trouble, and it's probably going to say it's running OpenGL 1.1. So just make sure you've set up and initialized GLEW correctly. And it's even told me what version of the driver it's running, which is kind of cool. Okay, that's great information. What might be nice to do there actually is comment out the GLEW initialization and see what happens. So let's just comment that out and see if I'm right that it will still find the old-fashioned Windows thing. Nope, it was okay. Okay, so maybe it's not such a big of an issue anymore. Oh, but no, it actually does that with the header, doesn't it? We could fiddle around. I think if you include like gl.h, it will find the Windows one. Sorry, it's not the initialization part. It's the header part that does that and resolves that issue. Okay, so you're probably okay. I think that's all right. We might print the graphics card as well. What am I going to call this device? What was that called? Renderer, I think, is the device. GL. Okay, so it didn't print that. What did I miss? Oh, it didn't actually do a printf. Okay. The device is. Okay. And this is going to be a nice little hint so you can check. If you're on a laptop particularly, is it running Intel something, in which case it's probably using my built-in thing. And it can be really annoying to get it to use the right graphics device. If you've, for some reason, the NVIDIA drivers look for your program by name and match it in their database of the .exe files that games use. And if you by chance have a file name that is the same as one a game uses, it will default to whatever that game prefers using. And some of them prefer using the built-in Intel stuff. And it's super annoying. So we can come back to, there are workarounds for doing that later. And I could do a side topic on specifically forcing it to use the NVIDIA driver. But it's definitely great to be able to print that out to double check. And it's told me it's using the GeForce, which is great. I'm not on a laptop, so it doesn't have that option to do a sneaky on me. But one of the really annoying things with NVIDIA is there is a game there with a .exe file called main.exe, and it doesn't want to use, it wants to use an integrated device to run that, which is super annoying because that is like your default .exe name with Visual Studio. um, so very annoying. The other thing I noticed today is if you build a Hello World file like we did called main.c and run it in Visual Studio and compile it, Windows thinks it's a virus and it tells you it's a particular type of Trojan. And this is something that like is a default for Microsoft's main software building platform, and for some reason their antivirus, presumably because it's old super intelligent genetic algorithm, or rather deep learning stuff now, it doesn't even have any ability to whitelist things. So very annoying, and it will just not run things, and then you need to go and dig around in Windows Defender to make sure it allows, what did I call mine? Stream live startercode.exe or whatever. It's super crazy. But that's software in 2020. Um, I had the same problem if I did things on the command line and built programs on Windows these days. So it's something has changed with the latest antivirus software that has made it incredibly annoying to build software on Windows. Do you need a good GPU for graphics programming? No. To get started, no. To do interesting stuff, not really. You could get away with learning a lot of graphics programming on even a little crummy integrated thing, as long as it does, and you will find out actually which version of OpenGL is running. if you can run even OpenGL 2.1 is fine for learning modern graphics. If that's all you can run, or you can only run WebGL, I mean, even a phone, even a budget phone will be able to run WebGL. So that's not a problem. I don't think it's a problem anymore. There was a point in time in the 2000s where you would have had to go shopping for a good one. Um, I don't think that's the case anymore. I think everything will have something that works enough for you to learn on. If you want to try specific features that are only available on the latest drivers, they require custom hardware. So if you want to do compute shaders and play around with them, you're going to need a reasonably recent GPU, but I think these days just about everything will do that. If you want to build a competitor to Doom Eternal, yes, you will need super powerful GPUs. If you want to just play around and make some cool stuff, no. And in fact, having some technology limitations and trying to build something that runs well on a not super powerful computer is probably going to make you a better programmer because you're going to learn what's slow and what's not. So I wouldn't worry too much about that. It's nice if you've got one, but do you need one? No. You're not even going to be able to harness the power of the latest gaming GPUs until you get very experienced in what you're doing. So I wouldn't worry about that at all. I am, however, going to add some brackets into this thing because that's really annoying me that it doesn't have them. I did a stream yesterday about C programming and I said several times, don't ever do things without braces because it's so easy to make a mistake. Okay, so one thing you will want to do when you're playing around is try and request different versions of OpenGL to see what your computer can run. And right now it's just using whatever the default create window, create context is giving it. You cannot rely on that giving you the latest version on whatever your computer you're running it on. It may just give you the oldest version if you run on a Linux or a Mac, which is not helpful. Um, so you want to be able to explicitly say, give me this version, if at all possible. And there is a command for doing that. I think it's glfw window hint, I think is the name of the function. And again, you can go looking through all the functions in the glfw documentation. Here it is. It has great documentation. It'll tell you everything. It'll give you a guide to starting a window. It'll give you a guide to starting a context. And I think window guide is what we want because this is going to include the hint stuff. Yes. Okay, so there is a hint function there, and if I click on that, it'll give me a list of stuff I can do there. Parameters, okay. So where are they? Give me the list. There should be a version parameter in here. Okay. Yes, this is what we want, these two. GLFW context version major and context version minor. So we're going to need to call this twice. I'm going to copy paste that. So what the OpenGL breaks down its version into two parts. So there's a 4 is the major version and the 0.1 is the minor version. So we're going to ask for both of those. So first is that hint. Second, I'm going to ask for 4. And then I'm going to copy paste this again and then do minor. What's the name of that other enum? And then 1. So I'm going to try and get, and this is the default you should try and do. 4.1 and then see what happens. And yes, it successfully started 4.1. If you're on Mac, you might need to also say, give me the core version of the context. I'll just see if I can find that on GLFW core. And that's like saying, give me a version of OpenGL that cuts out all the old stuff. Doesn't let me use old functions. Okay. And I think this has changed a bit recently. Okay, so I need to give it OpenGL profile as the first, and then GLFW, was it context core? No, core, what did it say there? Core profile was the name. Okay, let's try that. That should give you a much more likely to work on all platforms version of OpenGL. So this should work on just about everything. If it doesn't work, come and fiddle with these numbers here. And if you want to try and see what the latest version that runs is, try and fiddle with these numbers until it stops working. So if I try 4.7, which doesn't exist, it should tell me didn't work. Yeah. So unfortunately, although it's a hint, it won't. work. It won't fall back to the first working version, which is a bit unfortunate. It will only it will work or not. So if it doesn't have the version you ask for, it won't work, and that can be a bit painful actually. So you could, check if it works, see if create window works, and then if it doesn't, try a lower version. You could do that if you wanted to make more portable software that just ran. The way I solved it was on Mac, I defaulted to one version, and on Windows, I defaulted to another version. So I didn't do a fallback thing. And then if you were running it at all, you could switch between versions and start again. Hello, Lidborn. Okay, there's another flag there which you kind of used to need to put in. I think it was like a Ford compatible profile. I don't think you need this anymore. I think they got rid of that in a recent um, version of OpenGL. So I think that's only valid in older. Where did I put my own website? I have this on here somewhere. So, okay, somewhere in here, I actually wrote that down. Okay, so there's a thing you used to have to do here, core profile. You also used to say, give me a Ford compatible profile. So I think that was only valid up to like OpenGL 4 or something, and then they got rid of it because it was weird. Um, but that was a very clunky additional mechanism for saying get rid of all the old stuff. And that's a nice thing to do because so the OpenGL API has all of this backward compatibility notion that you can still use all the old stuff and they want to support all the really ancient commands and features and things going all the way back to the beginning. I don't know why. I think this was a bit of a design mistake by the consortium around about the time they were transitioning into a shaders only API. They didn't want to let go of the old things for some reason. And that has been a huge source of confusion for people. So if you go around looking at tutorials on the web now, some of them will be old and out of date, but they'll still work. But what you're doing there is there's a lot of tutorial stuff, and it'll be GPUs only draw triangles, but a lot of tutorials will use older function calls that'll draw rectangles called quads, or lines, or dots, or points. And these kind of things aren't properly supported anymore, and they might work, but there's a very good chance they kind of won't on some computers, or it'll be really, really slow and clunky and like a forgotten, poorly maintained um, interface. So that's really unfortunate. So what it's really nice to do is explicitly get rid of all the old stuff so you can't even use it by accident. And that's what these core and Ford compatibility flags help you to do. They don't get rid of everything, unfortunately, but they get rid of some of the old deprecated stuff. So if you look at the quick reference card, the reason you want to print this in color is because it actually has color coding to help you find the latest stuff and the old stuff. Um, yeah, so the purple stuff is from the core specification, which is the latest and greatest stuff. Use those if you can. The blue stuff is the compatibility profile. So those are all the old things that for some reason they haven't gotten rid of yet, but probably should have. All of these vertex commands and things. That was a way before we had buffers of data that copied into RAM. You would every time you drew something, you would specify every vertex one at a time and feed them in. So those are manually feeding in geometry every time you draw things, and it's still in the API as you can see in OpenGL 4.1, and it really should not be. So all of these things avoid the blue bits. Black fine, purple fine. I don't see any purple stuff actually. It occasionally tells you what version something is from beside it, which is nice. Um, black fine, beware the blue stuff. So that's a really nice thing about the quick reference card. And if you're unsure, go and check docs.gl, and it'll split things down by version as well. You may also have to, every time you come across a new OpenGL function, look it up. There's also an OpenGL wiki, which you can look up, and it will give you a bigger discussion about which version things were introduced in, if they were a little extension, which is like a experimental plugin, or at what version of OpenGL they were made core. And that should be able to tell you, hey, to use this function, do I need an extension, or can I just use it from the main interface? So the wiki, docs.gl, and the quick reference card should be your primary references. And then if you get really confused and need more information, you can go and look up the specification document, and it'll have a page on it, everything. or just ask someone is probably a much more efficient way to do that. Ask an OpenGL programmer, and they will give you the, oh, technically that's in the latest version, but unofficially that's something you should never use. There's a lot of that stuff, unfortunately. Okay, so that's kind of taken us ages so far, I think, unfortunately. Time is so that's yeah, we're like half an hour in. And all we've done is start OpenGL, but this is a significant milestone actually. We've also started a window, which is nice, and linked in some libraries, which is always painful. So we could take maybe a 5-minute break, largely because I want to drink more of my coffee. But if anyone's got any questions at that point, or if you've actually tried doing this while I've been streaming and you've got some error you want me to give you a hint on, we can do that. I forgot a little quirk with GLEW. There is a little flag we might need to set to use the latest OpenGL functions, and it's GLEW experimental equals GL true. That may not be necessary anymore, but I'm going to err on the side of caution once again and just put that in. Just make sure we can. It might have been fixed in the latest version of GLEW, I don't know. Use the latest functions from OpenGL like vertex arrays. Yeah, so just to recap there, when you're doing your includes, GLEW header first, then GLFW. But it's actually the reverse order for initializing things. So initialize GLFW first, add your version hints, create your window. So the hints go to the window, so do the hints before you call create window. Then call make context current. Oh, whoops, I put this in the wrong place. And that will create an OpenGL context, tie it to the window, then initialize GLEW, and that will then let you pull in extensions and stuff, which you might want to do later. After that, you can start calling OpenGL functions like glgetString. So, okay, I think we're ready to draw stuff now. So drawing, you can draw once, but normally speaking, we want to do some sort of animation. We want things to move around in our display. So we typically have a while loop in our program somewhere called the main loop or the frame loop, and we draw one complete image at a time, wipe everything, and do another one. So that's analogous to frames in the movie industry. Okay. And there is, so to stop the while loop from going forever, there is another GLFW function that will tell us if the user has clicked on the little X to close the window. So we can actually put that in here to stop the while loop from entering an infinite loop. So while window should close, and then give it the variable name that we had for that window pointer. Okay, let's see what happens. Okay, so it's given us our window, so that's new. However, I think it has entered an infinite loop there. Or it could just be a little clicky Visual Studio thing. Nope, I think it's entered an infinite loop. So if that happens, click the little red dot button. So I think I'm missing the window update function that will let me actually interact with it. And there, if we put down the end of our loop, glfw poll events, that will do things like update keyboard input and anything that the window needs in its operating system update or event handling, which you will know about if you've ever made a Win32 window directly, which you should do once at least. Microsoft has a pretty good tutorial for creating a Win32 program. Let's actually put a couple more commands there. So every time this loop runs, we're actually drawing one complete frame. So we're clearing the whole image every time we draw, then drawing our stuff, and then putting that image into the window. So what we want to do at the start of our loop is actually wipe the background image every time. So I'm going to go actually GL_clear is the name of the function to do that. And that has, again, we're going to look that up in docs.gl, which should be your go-to for looking up each function you use from OpenGL. Starts with GL, therefore it's from OpenGL, GL_clear. And OpenGL 4. This function hasn't changed in forever. So it has a bit field mask it takes as an input. So if you've never used these before, I'll give you an example. We don't really need both yet, though. We can do it. So it takes these inputs as little bit masks. So we can clear the background color, or we can clear the depth buffer, which we'll need when we actually do 3D stuff. And that's another image which says for each pixel in the window, which things are closer to the screen so that it knows what things to draw on top of what other things. It's an algorithm called the depth buffer or depth testing, which most 3D graphics uses. So we'll use that later. We don't need that yet, but we can clear that too, just so I can show you how a bit field mask works if you've never used one before. What we do, however, want to clear is the color buffer bit. So I'm going to copy paste that and paste that into there. So if we wanted to clear 2 of these bit masks at once with the one call, you could do 2 separate calls with a different thing in each. Or if you use the bitwise OR, which looks like the logical OR, but instead of 2 of these little pipes, we have just the one. And then we're going to say GL depth buffer bit was the other field. Okay, so that will do both of those things. What it does actually is combines both of these flags into one variable. It sets 2 bits in one variable and passes that as an argument to GL_clear. So that should hopefully give us better control over our window and also clear the background of it every frame. Hopefully it does. Okay, so it doesn't look like it does anything yet, but hopefully we can close it if we click this button now. Yes. Okay, and I think it was just missing the poll events function to let us do that. Wouldn't it be nice if we could set the background color of the window? Turns out we can do that too. So if we go to docs.gl, it might actually have a link to that here. Yeah, there's one here called GL_clear color. For some reason it doesn't link, but we can type that in and go to the OpenGL 4 version of that. Okay, so this is the function we need to call to set the background color. Whenever we clear it, this is the color it's going to have. And it has 4 components, 4 floats. GL float, again, that's just going to be a typedef of float on just about every system imaginable. So we can just give it floats as arguments. So I'm just going to copy paste this. It doesn't return anything. And you don't need to set that in your loop. You can just set it once and it will retain that value forever until you call it again. So I'm going to give it, so it's got red, green, blue, and alpha. And there are different ways to represent colors. 3D APIs, you might have seen colors in hexadecimal for the web. So you have things like 00 or 0.00, 0x00 for hexadecimal notation. But usually 00 is like black, and FF is full color. So that's 0 to 255, right? It's that range, but in hexadecimal. 0, 0 to FF, right? So those are two different notations. This is like decimal. This is hex, which is used on the web a lot for colors. So you'll see things like 00FF00. And what that's actually doing is it's saying there's no red component to the color. There is a fully green component to the color and no blue. So it's a full bright green color, right? So we actually have that same split of channels. Um, but for 3D graphics APIs, you typically use floats between 0.0f and 1.0f, or 0 and 1, right? So we're going to use those. So if we wanted to clear the background to a kind of gray color, and it's a good idea to use a gray color, that means if anything's rendering black, which can happen if you make a mistake somewhere, you're still going to see something. You're going to see the shape. If we do a black triangle, it's still going to show up on a gray background. If we have a black background, it won't show up. If we have a red, colorful background, it's going to drive us insane. So let's do a gray color. So we could do red, green, and blue. Okay, so we're going to do, let's say 0.2, green 0.2, and blue 0.2. So it's just a dull gray. Um, Maybe even a bit brighter would be nice. And then there's this alpha channel. It doesn't really mean anything for us in Clear, so I'm just going to leave that at 1.0. It's often used to represent opacity. Um, by default, doesn't do anything, I think. You can, I think, set things up so if you want your window to float around and have a transparent background, you can have that do meaningful things with transparency. But I don't think for us it's going to do anything. Oh, that's not what I wanted to happen. Okay, so Windows Auto Formatter is a bit mental, but okay. Hopefully that gives us a gray background. It does not. We're missing a command there, aren't we? So when you're drawing stuff, you have a double buffering system. So if you've ever done old school graphics, like you've run a game on like a ZX Spectrum or something, whenever things get redrawn on the screen, um, you will see the sprites like pop in one at a time, and then you can start playing, and it's really weird. And what that's doing, that's a single buffering approach. So every time they draw something or something moves into a new position, they have to redraw it, but you will see them pop in one at a time. And it's really amusing to see old arcade machines and things that do this. Very odd effect. So to avoid that weird effect, double buffering will actually have two screens, and we have one hidden in the background and one we display to the people using it. And while we're preparing a screen, we still have to draw everything one at a time, but we don't show that to the people using it until we're finished, and until we finish drawing a frame. And then we have this notion of swapping the two over. So we only ever show the completely prepared version of the frame, right? And when we're ready, we'll swap the buffers over, and we'll have a command called swap buffers, and we'll show the finished one, and then the other one will wipe it again with clear and start drawing our next frame into there. And when that's ready, we'll show that. So you have one that's presented and one that's hidden. So right now we're only drawing to the hidden one, so nothing's showing up. So after we've finished, we've cleared and drawn whatever we want, draw stuff in here, we need to actually present that at the end. So I'm going to, at the end of my frame, I'm going to say glfw, and again, that library has a command to help us do that, to tie it to the window. I think it's called swap buffers, yeah. And then we need to give it the window pointer again. Okay, so that should actually do that for us so that we can see things. Yes, so now we've got our gray background. And if we really wanted to, we could animate the background and do fancy color changes and things, but I'm not sure I do really want to do that. So that's nice. Now we have a starting point to draw stuff. We know that we've got a nice new version of OpenGL running. We know what we're stable for. Lidborn, you're very welcome for the nice lectures in Sweden. Done with the exam and project. That's excellent. Excellent news. So we did, this was in December. I did a few lectures at a university in Sweden, and we did intro to graphics, but we were using DirectX or Direct3D 11. Or was it 11? I think it was 11. Yes. It wasn't 12 because that's a little bit more complex to get started with. I think previously we'd done 10. So very similar to what we're doing here, but with Direct3D. Okay, so that should give us enough. So what we want to do now is draw our first thingy with OpenGL. And typically a triangle is the first thing you draw because that's the simplest primitive that, simple shape that a GPU will draw for you. If you could draw, they say if you could draw one triangle, you can draw as many as you want. And actually, if you try to draw after you've drawn one triangle, try and draw a million on the screen in different positions is a very good exercise, and you will be impressed with just how powerful your GPU really is. Because you will definitely be able to draw a million triangles on most, even probably your phone can handle that these days, which is really cool. Okay, so let's think about a triangle. And the way we usually define shapes is a little bit surprising for most people. I have a picture I want to show you. So, boom, boom, boom. Okay, so this is from one of my terrible diagrams. So what we're going to do is try and draw a screen that looks like this. So we have a triangle in the middle of the screen, and this like rough border around here, that's supposed to be the window, rather. So rather than this, when I say the screen, I mean the window that we have open. So we want a triangle to sit in the middle of the window. You can change this around, so have your first triangle take up half the window or whatever you want, or the whole window, it doesn't matter. But as long as we see a triangle, we're doing well. And it's a great idea when you're doing this stuff to get a pen and paper out, because once you can draw what you're intending to code, it solves so many of your problems. It's a geometric subject. You're thinking about shapes a lot, what shapes are in front of other shapes, which way around things should be. It's really easy to work out the numbers to go with that once you have a picture. So I highly recommend drawing on some grid paper or something every little problem you're trying to represent with your code. And so I would start with this. And the way we represent shapes is defining them not by like every point on the surface or anything. We just give the three surrounding vertex points. So a vertex in geometric mathematics is just a corner point. The plural is vertices or vertexes if you prefer. And we're mostly working in 3D space. It is possible to work with 2D, but we're mostly interested in working in 3D space. So we are going to define a position or a coordinate in three components for each vertex, right? So we have a top, which I'm using vector notation there in a column, which you may see, but that's the same as saying an x value, a y value, and a z value, and you do that for all three, right? And we're going to be drawing to our default coordinate space that we give 3D coordinates to um, OpenGL when we're finished drawing things and animating them. This is the coordinate space we're going to be using. It's actually called homogeneous clip space or homogeneous clip space or just clip space. Don't worry about that yet. Coordinate spaces you can come back to later, and it gets very interesting. But and it doesn't really matter what convention you use, but when you finally give your output to OpenGL, it has to be within this range of coordinates. And so you have this concept of a volume of space, and anything that's within the coordinate space of this volume is visible on your screen or in your window. Anything that's outside of that gets clipped or culled out of view, right? And the default dimensions for this in OpenGL are a little bit different to other APIs, but they're all fairly similar. The conventions change a little bit. You have three axes, right? So we have an x-axis horizontally on the window on the bottom with -1 for the left-hand side of the window, 1 for the right-hand side, um, and the y-axis for the vertical with 1 at the top, -1 at the bottom. So if you've used image drawing software before, you typically have 0 at the top and 1 at the bottom. So it's a little bit different to that. And then we have a 3D space, and this is in and out of the screen, and that's your Z axis. And with OpenGL, the direction going into the screen is negative, and the direction coming out towards you is positive. So halfway in between that allowed range is 0, and the furthest distance away that will be visible is -1, and the closest or nearest distance is 1. So that is your like default coordinate space or viewing volume that everything has to fit into. If you give your triangle coordinates that are outside of that space, they're going to cut off part of the triangle or the whole triangle won't be visible, right? So we want to give sensible positions within -1 and 1 on every axis. So to have a point right in the middle of the display near the top, I am giving it an x value of 0. So 0 is halfway between -1 and 1, right? So that's our first value for this point. So it's x is 0, y is 0.5. So it's a little bit up. It's halfway between the middle and the top of the screen, right? And then the z value is 0. I want that. I don't care. It's just going to be more or less a 2D triangle to start off with. Um, so we're not going to worry about the depth. 0 is in the middle of the visible range. So 0 is fine for z. And what I'm going to do is proceed in a clockwise direction. And I've got these little arrows here going dot, dot, dot. You don't need to record anything for the arrows, but the order that you give each point in is meaningful. So just remember what convention you're using. It's okay to go counterclockwise or widdershins if you prefer, which is I think the old English term, but you have to be consistent. So most OpenGL stuff, you'll find it more convenient to actually go counterclockwise because more 3D model file formats and things go counterclockwise. That doesn't matter. Right now, it doesn't matter at all. And you can actually switch between conventions, but try and keep it consistent within a thing you're drawing. So we're going to go clockwise, and you got to remember this. Um, the next point is going to follow that one. So this is our first point. The next point is the next one in clockwise direction. And it's going to be 0.5 on x, so halfway from the middle to the right-hand side, minus 0.5, so halfway from the middle downwards towards the bottom, and 0 on z again. And similarly for the last point. So that lets us define a triangle 0, 1, 2. Okay, so we're actually going to create a buffer with those 3 points in it. If you wanted to, you could create some. I'm just going to keep that image open here somewhere if it's possible at all. Let's see. Okay, I'm going to have to do some fancy stuff here. Okay, I think that worked. You could tell it was a really heavy drag. Okay, so what we want to do is record these into an array of floats. So you can see there's a decimal point there. An integer is not going to work. We're going to do it in a float. And so I'm just going to make an array. You don't need to make a fancy data type to store 3 things all together. You could if you wanted to. It's just kind of going to slow us down. So we're not going to touch that yet. Let's just make an array somewhere. So I'm going to do it before we start drawing. You don't need to, an older OpenGL, you would need to feed this in every single time you drew everything. We can just define it, put it in a buffer, and as we mentioned, copy the whole thing to graphics memory. And we don't need to touch it again, which is great. So I'm going to make an array of floats called triangle vertices, let's say. Right? And then the first point for x for the top point there, this is where we're going to start. This is point number 0. So I'm just going to drop this down here. I will split it line by line to make it easier to read. So x is 0, right? The y coordinate for that first point is 0.5, and the z is 0. So that is the top point. Okay. Then the next one in clockwise is the one in the bottom right. And you could make your triangle a different shape when you start this off. I mean, you should definitely try fiddling around with it and make a different shape if you get this working. So 0.5 for x, minus 0.5 for y, so further down the window, or the drawing area within the window. Okay, and 0 on z, so that's the bottom right. And then the last point there is minus 0.5 on x, minus 0.5 on y, and 0 on z. And we don't need the comma at the end. So that's the bottom left. So clockwise. And you call this a winding direction in graphics? Winding order triangle. Okay, so that's the reason that's meaningful is the order we give them in helps us. It gives us, or at least it gives the graphics API, a way of saying which side is the front and which side is the back. And there's a nice optimization you can do. So usually, if you have a 3D model, you never render the inside of the model. Only the outside shell is useful for drawing. So there's an optimization built into graphics APIs called back face culling, and if you tell it that either the clockwise or the counterclockwise direction is the front, then it can automatically not bother drawing the reverse side of the triangles. You won't see them anyway, so that will speed things up for you when you're drawing. So this is helpful for backface culling. That's one algorithm it's helpful for. I'm sure it'll be helpful for the other things too. Okay, so now we have everything we need to represent a triangle. That's it. You don't need to do anything fancy at all, just the corners. The graphics API, when you draw, or the graphics driver on the hardware, will go away and fill in the actual pixels in between those coordinates for you. You don't need to worry about that at all, which is great. And the problem now is that this is just sitting in our stack memory somewhere. So this is the CPU's memory, the main memory of your computer. This is not memory that the GPU can access. So your graphics unit is actually operating asynchronously to your CPU. They don't always talk to each other. One wants to run as fast as it can. It's not going to stop and wait to see if there's something the CPU's got for it, if it doesn't have to. And when you do pass information to the GPU to say, here's my list of triangles for you to draw, or here's my one triangle for you to draw in this case, you need to explicitly tell it, hey, I want you to copy some data over to a buffer in your memory that you can use. So there is a system for doing that in OpenGL called a vertex buffer. It's the same thing in Direct3D. They use the same kind of mechanisms because the hardware has driven these things closer and closer together over time. Okay, so we need to put this into a vertex buffer for the GPU to access. And now presumably OpenGL will put this in VRAM in the graphics card's memory. It has a little onboard memory that's really fast and it can use it. There's no guarantee of that, so it may just keep it into main memory until it needs to draw with it. It doesn't tell us, so we don't have that transparency. As far as I'm aware, you don't get that information at all. So that's okay. We normally don't care as long as it draws something for us. For our basic use cases anyway. So what do we need to do that? So OpenGL has this really bizarre interface. So when you create an instance of something, we want to create a new buffer, right? It's not an object-oriented API. It's a C old school API, and it has two unusual concepts. First of all, when you create a new instance of something, it doesn't give you like an object-oriented programming would. It's not an instance of a class. It's not really a pointer. It gives you a handle to something, which is usually just an integer. And that's just what you call it. It's what you call an opaque pointer. It's actually a really nice interface design idea in general. I don't know if OpenGL's version is a very good way of doing that, but it's okay. But it might be a little bit of an odd concept. So the first thing we do is essentially request a handle. And it's like a unique ID we'll use to refer to our thing. It will keep in its memory somewhere the actual memory with the thing. We don't touch it directly. We just get a handle to it. And then whenever we want to actually copy memory to it or get memory from it, we'll say, hey, can I put memory in this? Here's my unique handle ID you gave me to refer to it, and track that it's still valid. So if you ever do API design, you might consider this idea. It's called an opaque pointer or a handle. But OpenGL calls these things objects, which is really really confusing for most people that have first done object-oriented programming. So it's not an object-oriented system. So I think the function we want to use is called glgen buffers, where we can get more than one if we want, and we're going to ask for one of those. And it returns an address of a GLU int, so it's just an integer. And that's a unique ID. I'm going to make that up here. So GLU int, capital GLU int, and it's probably, you could, if you wanted to, you could just go unsigned int. I think that would be fine. GLU int, I like to put the funny little typedef names that OpenGL uses, not because of like safety or anything, just it reminds me this belongs to OpenGL. And I'm going to call this a vertex buffer handle or ID or whatever you want. That'll do. I'll initialize it. That won't matter though. And then we'll give it the address of that, and it will set that for us. The reason it has a pointer is because we could give it an array of these to set if we wanted to. Now that I don't believe these, from talking to OpenGL people that work on this stuff, I don't think that actually generates a buffer or does anything like that. It just gives you a handle. Literally just gives you an integer to use with a reserved number. So hopefully that'll compile. Okay, I don't need to look that up. I think that worked. Okay, once we've got that, now we have another unusual API concept that OpenGL uses called binding. So again, if you've done object-oriented programming, this is going to be very painful. If you have not, if you're happy doing old school C, less painful. The idea is that you have global state in your context of OpenGL. So when you want to work with a buffer, for example, we now want to copy our list of vertex points into it so that we can draw with it. You cannot call a function with at least most of the API still works like this. You cannot call a function and say, here's the buffer, the handle of the thing I want to use, and here's my data. You first have to say, please bind is the keyword there, GL bind, and I think it's just bind buffer, right? And we tell it what type of buffer it should be and then give it our handle. And what that means is that every time we call a buffer operation from after this onwards, it will use that buffer that we have bound for everything, which means that if you accidentally forget to bind a new buffer, you can modify your old one really easily. It is not in any way encapsulated. So if you go away, like most students will go and make a little class framework, well, they'll make a buffer class and a mesh class and a whatever class, and they'll call these commands within what they think are nice, safe, tidy, encapsulated functions. They are not. So if you call buffer operations within a function within some class somewhere, and you have not bound a new buffer or unbound the last buffer, it's going to modify the wrong thing. And that can be very, very confusing for people. So global state is kept globally in memory, which thing you're operating on. And I think we want GL, is it vertex buffer? Let me double check. I'm going to go to docs.gl. No, that's not the one. Bind buffer, it's called. Not bind buffer range. Okay, so there's a lot of these functions that have bind in the name, and that's what they're doing. So target is the thing I wasn't sure of. Is it array buffer? No, I think it's, what's it called? Um, Maybe it is array buffer. It is array buffer. Yes, okay. Something I think APIs do very badly is they overuse certain terms to mean about 10 different concepts. So vector and array are two of those things that come up all the time, and attributes, incidentally. And you'll see why that gets confusing shortly. Okay, so array buffer, that sounds about right. And then we give it our handle. So that thing is now bound. And everything we do for the rest of the program will now use our buffer. If we wanted to use a different buffer, we would have to bind that first, okay? So there's a little gotcha. If you want to, and this is probably a good idea if you're writing functions and stuff, you can unbind things by giving the value of 0. So that will let you unbind. And then if you call another, unbinding, unbind. If you call another buffer operation after this, it will crash or give you some error or something, which is a nice, oh yeah, I forgot to bind my buffer. So that's a nice little thing you can do there to help encapsulate things. So now you could say like, okay, all of this stuff is, all of these things are essentially together in a function or a block or something. So you're nice and safe. Okay, so there's another command called, to actually copy that stuff in, it's gl buffer data, I think, buffer data. Okay, and it wants that same target idea. It's an array buffer. There are different types of buffers. This is the one we're using at the moment. It's an array of vertex points. It wants the size and a pointer to the array and the type of usage. So let's look up that function here as well. Okay, size in bytes, that's fine. We'll just give it at least enough space to fit our array of floats. And the usage, we just want static. We don't need to change this buffer ever, so we can just say static draw. That's fine. There are lots of different options. If you update your buffer and change the geometry a lot, there's stream and dynamic and different options there, and you can have a look at what they all mean. So that's the last parameter. So what does that have there? So the second parameter is the size, and we can say size of float, and it's 3 xyz times 3, so 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. That looks about right. What was the next parameter? Was the actual data, wasn't it? So we could just give it that. I don't think we need our triangle image anymore. Okay. I haven't checked the chat for a while. Is that okay with everyone thus far? I think that's right. That won't do anything yet. Let's see if it builds. Okay. Now what we need to do before we can draw it, we need to have another thing that describes this data layout. So we've just given it, oh good, I'm glad that's making sense. Hello, super megabyte. Okay, we need another thing now. We've just given it a block of data. It doesn't know how to make sense of that yet. It doesn't even know it's floats. We haven't told it it's floats. We haven't told it it's 9 of them. We just told it how many bytes are in that. And it's just dutifully gone away and copied that somewhere. So we need another thing that describes the layout of that data, because there are many different ways we could have laid out this buffer. So there's another thing, and this is the worst named thing in the whole API, called a vertex array object. So this thing is a vertex buffer object. You know what? I'm going to put object there instead of handle, so I get the terminology right. It is generally called a handle in most APIs. OpenGL calls it an object. Okay, so this thing is another uint we need to request. Vertex, and this is where I'm talking about overusing the terms array and object. Vertex array object, okay? What they should have called this is a vertex buffer descriptor, or an input data descriptor, or something like that, because that is what it is. It is the array is really unhelpful. It is an array of description things, perhaps, or a set of fields, but that's not helpful. It's very confusing, because this is an array. And this is the only thing I would describe as an array, as an actual array in the C programming language. There may be an array in there, I don't know, in different implementations, who knows. But that is the name of it. Very confusing for people. So this is a VBO, this is a VAO. You can see how there may be some confusion here. So it's GL, I think it's Gen, now let me get this right. Is it called Gen Vertex Array, something like that? No, that wasn't it. Let me refer to my documentation again. I often check my own writing for how to do these things. Gen Vertex, it was called Gen Vertex Arrays. Okay, and it has the same layout. Gen Vertex Arrays, so we tell it we want 1, and we're going to give it the address of the one thing. Okay, please set a handle to that. It doesn't do anything yet, it's just given you a new unique ID to use to refer to things. Right, and we're going to copy this. We're going to kind of put a block there just to help separate this out. So blocks start at a bind and finish at an unbind, and now it gives you a nice way to separate things and be sure that you've encapsulated stuff. So you don't need to be this tedious if you don't want to. You don't need to unbind things, because we're only going to use one buffer and one vertex array in this example, but maybe that's helpful for later when you try building a bigger program. Okay, now this is a little bit tricky, so I'm actually going to copy paste what I've got here and then explain that. Okay, so the first thing we do is bind the thing we've just generated, right? So we have that same convention, and then likewise we can unbind that at the end, just to make sure that nothing is happening where we don't intend it to. So it has a bunch of stuff in there that's a bit confusing. So the first thing it does is enable vertex attribute array. So now they've used every possible overloaded technical term imaginable all in one. And what they mean by that is we have, when you're drawing something, your shape or your geometry has a number of essentially input variables. We only have one in ours so far. So we only have a position for each vertex. You could have other stuff for each vertex. You can have colors, you can have normals to help you with lighting, you can have whatever you want. You can make it up actually. And I use them for all sorts of fancy stuff. Right now, we only have one, and you need to explicitly and enable and disable those attributes. And the first one is number 0. So that's what's happening there. And enable the first input variable. So right now we're saying there's one variable in this data, and please enable it for use when I go to draw with it. And that value will be stored inside this vertex array object we have bound. So anything you do here, these commands apply to this VAO, this vertex array object. Now remember that is just a terrible name for a data descriptor. It's saying what layout does what I'm going to draw with have? So I expect this to be XYZ, 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 right? We're going to tell it that. But how many inputs are in there? Right now we only have one. It's just position X, Y, Z. So we're saying, please enable that. These will be associated with this thing that we have a handle to. So whatever you put in here is remembered in there. We don't need to do this every time we draw. We can set it up once. This is the worst part. This is the worst part of the API is the VAO. It's a modern concept that's supposed to save you some time. In older versions of OpenGL, this didn't exist. You didn't have a VAO. And if you've ever used mobile OpenGL or WebGL 1, which I think is still the best supported WebGL. There is a WebGL 2.0 now, but I don't think it works everywhere. At least it didn't last time I tried. You don't have a vertex array object. You could sort of unreliably maybe get it as an extension. So what you would have to do is every time you draw stuff in your loop before you draw it, explicitly enable these things. So say enable one vertex input, enable this, enable that. This is the layout I'm going to draw with. So the VAO, the vertex array object, was like a I don't want to do all this tedious stuff every time I draw. It would be nice if I had an object that stored this state. So I could just say, use all the state stored in this object. That's what it's for. Very, very poorly named, very poorly described. That's the point of it. It will take you ages to figure this out on your own. It's handy to have someone who knows what this is supposed to do. And people have very strong views about these things. Either it shouldn't be in the API at all, I don't like it, I'm just going to have one global VAO and then do this stuff every time I draw anyway and always keep this bound. Some people do that, and actually some people are convinced this will be the best performance, but then I've seen like whole blog posts about people that work on the drivers at AMD or wherever that say, no, that's not the intention, and here's a chart to show that isn't actually true. But it doesn't matter. People will do it the way that they insist on doing. So you have options there. I try to follow the advice from the people who write the drivers because I don't know what's going on in these proprietary drivers, so I'll just trust them. Um, and every time I have a unique shape I want to draw, I'll have one of these vertex array objects to describe it and just carry it around with the shape. That's not really how the driver works underneath as I understand it, but it seems to be the most convenient way to deal with these things for me anyway. So I will have one of these for every new unique 3D mesh I make. If I want to draw the same triangle in more than one place, I still only need one of these because it describes the same data and I'm just going to change its position. That's fine. But if I have a triangle and a square, I'll have a new VAO for the square. If that follows, I hope that makes sense. This is the worst part of the API, so I want to get this right. Okay, so we've enabled attribute. Tell me if that's confusing you, and it probably should confuse. You have to do a similar sort of thing in Direct3D, but it has possibly a better name. I think it's even called a descriptor or something. Yeah. Okay, hopefully it makes sense as we go. So what we're doing is we're saying, okay, I want this vertex array object, this descriptor thing. This describes the data's layout that we are going to draw with. I would have called it a data descriptor. I feel like that's better, or a vertex descriptor or something. So enable the first input. And that is vertex position. And then the second thing is we're binding this buffer we created that has this actual stuff in it. So our actual 3D points. We're saying we're going to use this. So I'm going to put the correct variable name in there. We're going to use our triangle vertices. And we're going to say, I would like you, Mr. Vertex Array or Mrs. Vertex Array object, I presume married, I would like you to point into that buffer's data. So we create this new function called a vertex attrib pointer. So attrib is short for attribute, and attribute is the same name as an input variable for drawing. So input variable equals attribute. You don't see that so often. It used to be the name for input variables for drawing. Input variables for drawing, e.g. whatever is stored in a vertex, i.e. our position. Okay, so we have one input variable, that's an attribute. So our vertex has attributes. Ours just has one, it's a position. We have to say enable it, and then we're going to say where to get the data from, and we're going to describe what's in it. It doesn't know that we have an X, Y, and a Z. We might have an X and a Y. We could have got rid of the zeros if we wanted and just given it X, Y data. So 2 components per vertex. That would have been fine. So what we do is we say here, okay, I am going to describe input number 0, the first one, right? Input number 0, 0 and 0. These match. These correspond. Um, it's easy to mix these parameters up, unfortunately, because they're all integers. So if you get something wrong, just pick through every little parameter again. So the first thing is, for which input variable are we describing the data? So you might have more than one thing per vertex. You could sort that out here. If you had colors as well, you could maybe put, okay, input 1 we'll do afterwards. That will be the colors. But we're doing input 0. And it has 3 components, an X, a Y, and a Z for each vertex. And you can see we're just describing the layout of this array, right? And each one of those is a float. And we don't want it to do, I think that does like a transposition or something. Let's actually look this up on docs.gl. That's the smart thing to do. Okay, so we've got vertex attrib pointer. So it has an index. That's the yeah, not a great description. It specifies the index of the generic vertex attribute. So attribute is again that input variable to the shader, and it's the same thing we're enabling. To be modified, the size is the number of components. So components are your X, your Y, your Z. Or if you had colors, it would be your red, your green, your blue. And we had 3. It must be 1, 2, 3, 4. There is a type, and we had floats. You could have a different data type there, but be careful with that. Floats should be your default for just about everything you do in 3D graphics. It gets a little, there are different variations of these functions. If you want to use integers, there's another one here, I pointer. It took me ages to figure this out the first time I tried to do it. Just use floats unless you have a specific reason not to. Oh, it will try, there's an option there to normalize things. I don't think you ever need to do that. So you can always leave this GL false or just use false. The bool keyword should work. The stride describes the layout of memory. We have everything tightly packed in our array. If you had like X, Y, Z for each vertex and then a color, you would maybe have to jump over the color to get to the next XYZ. We don't have any of that stuff yet. We'll come back to that if we ever make a more complex demo with colors and things as well, which is probably the next demo you would do. Then we would need the stride. And null is just saying start at the beginning. What did it say there? Pointer. So that's where the pointer to your data is. And we're saying start at the beginning. You could give it an offset there if your actual data for position started later in the array for some reason. Okay, that is it. And because we've bound our buffer, maybe we'll play it safe and actually unbind it. So we're binding it so that this vertex attribute pointer knows which buffer to point into. Otherwise, it won't work. Okay, we could have just left this one bound, but maybe it's good to be explicit here and bind and unbind things explicitly every time. So it's doing this, right? It's saying bind this so that this thing can use it, and then we'll unbind it again so we don't accidentally use it somewhere else. You don't need to be this careful, but maybe it's better to explain it like this. Okay, now I think we have data that we can draw with. We're just missing one vital component. Okay, will that still run without crashing? Good, good. Okay, so key point, data describes what we're going to draw, and that is a vertex buffer. The layout of that is a vertex array object. It's the layout of our data. How many input variables are in the data? Are they floats? How many are there per vertex? Stuff like that. That's the VAO. When we draw, we do actually want to bind, and you only need to bind now the VAO. So I'm just going to bind that and perhaps unbind it again when we finish drawing. And inside, in between these, we are going to call the stuff we need to draw. I'll come back to that shortly. To do. Okay. So that will bring back, when we go to draw, it'll remember all the state we set up for which buffer to use. It'll know to use this vertex buffer. We don't need to bind that again. And it will know that it has one variable in it. Okay, now we're missing, so we've got the what to draw, we just don't have the how to draw. So we need to have a little routine that says what style it's going to be drawn in. Does it get animated? Does it have a specific color it needs to draw in? So I realize I've gone over time now. I was hoping to do this in an hour and I talked too much. But the style is determined by a little mini program that runs on the GPU called a shader. So the VBO and the VAO describe what data to draw, and a shader describes how or what style to draw the geometry. Okay, and that's kind of it. Once we have the shader, we're ready. So OpenGL uses its own shader language. It's made to resemble a C program, and it's called GLSL, OpenGL Shader Language. It was originally, I believe, just a copy of Direct 3D was first, I think, with shaders, and they had HLSL, high level shader language. Originally, these things had this little assembly like code, and it was really tedious. I think DirectX 8 was the first to do that, if I recall correctly. I may be wrong about that. But now you basically write some text in a string. You could write it in a file and load it into a string, or you could start with a string. We're just going to hard code a string. That's going to be our shader program. And it's a little routine to say there's two parts. There's a vertex shader and a fragment shader. The vertex shader says where to position each vertex, and we're just going to use our X, Y, and Z to do that for each vertex. So it will run once for each vertex point. So we have one vertex shader run for this vertex, one for that one for that one. And all it's going to do is say, use this input that we're going to give it as the position of the vertex. That's it. If we wanted to later, we could animate that. And every frame give it the current time it could use to offset the position. We might try that later. So vertex shader, position the vertex. Then we have a fragment shader. It goes together as a set, and that runs once per pixel-sized piece of surface. So when the GPU actually rasterizes, which means colors in the inside of our triangle, it will has a fill routine to actually create a pixel for everything it can identify as fitting in between those floating point coordinates, so it actually matches up 1 pixel to the resolution of our screen. It will work that out. And then once for every pixel-sized piece of surface, which is called a fragment, it will run a fragment shader, and that says what color should we make this. And if we wanted to, we're just going to say let's make it red or let's make it purple. If we wanted to do, we could do fancy stuff in there. We could do really interesting textures and lighting, and we're not going to do that yet. We're just going to say make it a solid color. So we need to make two little mini programs, stick them together, and then bind that before we draw, and it will draw with that shader. If we wanted to draw in a different style, we could bind a different shader. It's that simple. Bit of an unusual concept, but once you've got shaders, you can do anything. They are super, super cool. So we just need to make a string, two strings actually, one for each type. So uh, let's make a new block actually. Const, let's say shaders, char star, and I'm going to say vertex shader string. Okay, and then I'm just going to hard code it. And because it's going to have a few lines, I want to be able to split my string up. So I'll do a string literal. And to split it up, you can do this little slash at the end, I believe. I forget which way it goes. Maybe it's that one. Let's try it. Let's try it and see what happens. So it starts off at the start of your shader. You have a little version tag to say which version of the shader language you're intending to use. And usually the version roughly matches the version of OpenGL you're using. At least the modern versions do. So if we're using OpenGL 4.1 and targeting that, I'm going to try and use GLSL version 4.1.0. And I just happen to know that is the version that matches OpenGL 4.1. It varies a little bit in older versions. So to do that, you just type in 410. And that's a line all on itself, hash or pound version space, and then 410. If you need to run an older version of it is the other slash, isn't it? Yes, I think so. If you need to run is it? No, I think it is. I got it right the first time. Okay. It's going to complain about the same thing, isn't it? Yes. Oh, I never remember this. I'm going to check my one I prepared earlier. What did I do last time I did this? I didn't even do that. I did quotes on every line. So that doesn't help me remember at all. Does anyone remember on chat how to split up a string literal on different lines? I can't remember if it's forward slash or the other slash. Maybe it's Maybe it's that one. No, wait. /n is like that, so it must be this one, right? Okay, so let's try that and see what happens. It's not going to work, is it? Well, we can do this. Let's do that. And just do different quotes for every line. That'll be fine. So version 4.10, then what we do is we say you need to declare what your inputs are to your shader. And we had one input variable, and it has to match the data layout we've just described in our VAO, right? So the VAO kind of matches up your shader to your data. So we're going to say in, which is a keyword meaning an attribute or an input variable, in, and then the type of it we need to give. And GLSL, you should look these up on the quick reference card, has a bunch of useful built-in types for mathematics. And if we want to represent an XYZ value, we can give it a vec3 is the name of the type. And I'm going to call that maybe A for attribute underscore, just so I remember not to mix it up. And then I'm going to call it position, right? Because we gave it through an XYZ position. Then I think semicolon, end line, jump down to the next line. Okay. And then I'm going to give it, so this could be just be one big long string. You could lay this out nicely in a file. Yeah, okay, so it's backslash formatting. Yeah, I'm just going to leave it like this. I think that'll be fine. I'm going to put /ns in. You don't need to do that, but if your shader, you have to compile these shaders, interestingly, and the driver has a compiler for them. When you compile them, if you get an error, it can tell you, you can ask it to tell you what line the error was on, and if you put /ns in, it will meaningfully split your program up into lines. Otherwise, everything's just going to be on line 0. So I'm leaving them in for that. I'm not going to check for errors yet, but I'll try this. So you have a void main. It looks similar to C, right? That's it. And you can close your main function. And then in between there, we're going to do some stuff. And there's a built-in variable called GL underscore position with a capital P that you have to set. And that actually takes an X, a Y, and a Z and a W coordinate. So we can't just give it a position. We have to modify that a bit first. So if we check for errors, it would complain about that. So we need to give it a vec4, and you have a little constructory thing you can do. So you can give it your XYZ in one go. It'll accept that as the first 3 components, and then give it the W. And I think we can just leave that as 0 and see what happens. Is it 0 or 1 that's the sensible default? No, I've forgotten. It is 1. It is 1 because it has to be divided by this later. I didn't tell you that yet. Yeah, there is a process that happens after the vertex shader executes for doing 3D stuff with interesting 3D depth and 3D cameras and things. And that's where this last component comes in. And what it does is divides your XYZ position by this. It helps you generate perspective in your scene. If it's 0, I don't think you'd see anything. So I'm glad I checked that. Because you'd get a divide by 0, right? So, okay. So we can leave that at 1. That's our sensible default. Once you get things working, try fiddling with this and changing it to 2 and 0.5 and see what happens. And then you should perhaps start to understand what it does. Okay, so that's it. That should be our vertex shader. I think that should be correct. And then we can make a fragment shader string. This is probably going to be easier for you to read if you put all of this into a file. So in which case it would look like this on its own. But a string is certainly easier to start building with. So if this was all in a file, it would look like this, right? So I've just stuck this all into one string in a kind of ugly way. And I forgot a /n there, of course. And there. Okay, so we have in vec3 position and then a little program that executes. And this is all it does is sets the position of the vertex. And we've just given it. Remember, it happens, it will get executed once for each vertex. So we'll have 3 vertex shaders execute. And each one will get the unique position. So this vertex attribute pointer we set helps us describe the data. And behind the scenes, it will just iterate over that. And for the first 3 floats in the data, it will create a vertex shader and give it this. The next time it comes along, it will create a vertex shader and it will go along 3 floats and give it this as this input variable. And the last time it'll give it the last 3. So that lets us, you would think you would just loop over those, right, in one program. That would make sense in C. The advantage to doing one instance of a program for each one is you could do them in parallel, right? So suddenly you have this super fast way of doing a huge number of these things at once at the same time. And your GPU is really, really good at doing floating point calculations in parallel, and it can do a huge number of them. So I think your floating point processors on the latest stuff is that you get like 2,000 of them that could potentially do 2,000 calculations at once. I don't know if that means you'll get 2,000 vertices processed at once. It's probably quite a lot less than that. But and it's certainly not the same as 2,000 CPU cores. It's more like 20 or something equivalent, but it's a lot. And you have really good parallel processing power. So because image-based stuff is really easy to parallelize into pixels or vertex points, it makes sense to have a parallel processor to do all that stuff. And that's what your shaders are for. Highly, highly parallel processing. So vertex shaders once per vertex. So we have 3 of them and once per fragment. And I couldn't tell you how many fragments we'll get because it depends how big your display is. If you had 2 triangles that covered your entire window, you could work out how many fragments that would cover, and it would be the same size as 1024 by 768. You would have that many fragment shaders run, right? But because we're covering like a section of it, I don't want to work out the maths for that. It's less than that number total. Um, Right. So you could tell actually the fragment shader is more likely to be the bottleneck because we have way more than 3 of them. So same thing here, version 410. I don't have any inputs to the fragment shader. So I'm going to just start with, actually we do need to describe an output variable because we need to set a color. I don't know why that's not built in anymore. You can have multiple color outputs. We just want one. So we do need to say out keyword, and then vec4, we're going to give it an RGBA color as the output. So I'm going to say O for output, I guess, frag color. There used to be a built-in variable called frag color, GL frag color, that looked like this that you would set, but they got rid of it. Presumably they wanted more flexibility. Um, Okay, so I think I can do copy paste. It has a main as well, but we're going to set our frag color variable. We're going to set vec4 again, and maybe do we have a request from chat about what color we'd like our triangle? Oh, good. We still have quite a few people watching, so I'm glad I haven't bored everyone. So purple, okay, so that gives us red and blue, right? So if we do, I guess, default 1.0, 0.0, 1.0, does that look okay? Or would you like a different shade? So if it's between 0 and 1, we could modify that to a different color if you'd like. Alpha, the last channel, the 4th channel, doesn't do anything yet, so you can put anything you want there. It won't. We haven't told it to do anything. It won't do transparency. It won't do. You can have it do a bunch of things. It's up to you to define what it does. I'm just going to leave it at 1, just in case we enable things later. 1 seems like it doesn't do anything. It doesn't matter. You can put whatever you want there. So that's R, G, B, and M for alpha. Okay, so we've defined some strings, but we need to feed those in to OpenGL, compile that into a shader program, link those 2 parts together. So you compile both of those strings into little mini programs, then link them together. So it's because they happen in stages, you position your vertices first and then you color them in. It's actually possible to pass information between them. So you can have all your vertex shaders run, and then actually you could have an output. So if you had a color for each vertex, you could set that in here and then throw that down to the fragment shader and create this interesting multicolored thing across the triangle surface. So you can output from this stage and input to this stage. That's possible. We don't need to do that yet, but you do still need to link these 2 together. They come as a set. There are other types of shaders you can throw in there as well. These are the 2 you almost always need to have both of these. Okay, so the interface for creating shaders is a little bit different, and I do have to double check every time I do this. So you would think you would do GL gen shader or something, right? But I think it's slightly different. GL create shader, so the API is a little inconsistent. So I'm actually just going to copy this bit from my tutorial. So what I have done there, I'm going to call this, so create shader. Let's go look this up on docs.gl. Is the first thing we need. That's essentially the same as what we were doing here with this convention, GL gen buffers. So I would have called it GL gen shader for consistency. I don't know why they departed from that convention. Possibly it was different people that made that part of the API. That's probably exactly what happened. So if we go to docs.gl and go to create shader, there's also create shader program, which we'll need later. It has a kind of a different setup, so it no longer takes a number of shaders we want to create and a pointer. It just literally returns one. So a bit unusual. However, what we have to do is tell it what type of shader we want it to make. So there's a compute shader, a vertex shader, a tessellation, control and evaluation shader, a geometry shader, and a fragment shader. So I want a vertex shader. So you have to do this twice, once for each of your shaders. So I've got vertex shader there, fragment shader on this second call. And I'm going to call this vertex shader object, because that's probably the name for it in OpenGL, and fragment shader object, right? The next thing we need to do is actually send that string over to OpenGL so it has a copy of it, because it isn't going to be able to read into this memory. So it's like, here you go. Whoops, I think the first parameter is the name of your object. So notice you don't need to bind anything here when you're calling shader source. It actually takes a parameter. So it is a wildly inconsistent API. We're giving it one string for this vertex shader. You could give it a bunch of strings for different parts if you wanted to split it up somehow. I don't think I've ever wanted to do that. Let's look that up. GL shader source. That's for copying your source code or your string for your shader over. It is called a shader object. The length, and I think you can leave the length of the strings at 0. I think that's fine, or null, and it will work it out. And then finally, you have to compile it. So there is a stage where you compile your shader. So it does actually get compiled into a little program for running on the GPU, and that's kind of interesting. What you should do if you want to make a fuller, better version of this program before you start fiddling with things is actually check for errors after compilation. I won't do that now because it's like another 6 lines of code or something. Check for errors, and it will tell you if you've like accidentally misspelled something, the same way as the compiler does for C and C++. So we give it both of those strings, compile them into separate programs, and then there's a stage to link them into a shader. Sorry, it compiles both of those. There's this terminology of a shader, which is these individual guys once they're compiled. OpenGL calls them a shader in the API. When you link them together into one thing that you can use for drawing, it's called a shader program. So if you see in the quick reference card, you got shader, which is the individual stages, vertex or fragment, right? You also have a shader program, one word in the API, for the linked stages, right? Which you can actually then use that for drawing. You can bind that for drawing. So we have another thing, and I'm going to make that variable out here so I can use it later. It's yet another handle, so yet another object. It's called a shader program object or something like that. I'm going to initialize it to 0, but I think we have the same funny little API there, which is like GL create program, I think it's called. It calls this a program. And let's look that up. Compile shader, but create program, and this will do a linking process. We will give it those stages. Okay, that's it. It just returns something. Oh, there's an example here, actually, which is nice. So you've got some reference code on some of the articles on GL docs. So you create your program. We once again have to tell it what the inputs are and what the names are going to be in the shader program. So I might just copy paste one of these lines. You know what? I'm going to copy paste all of that. It will tell you how to check for errors here too. If you want to go away and do this later, just make a note of that. The GL create program page on docs.gl has a great example. If you want to do a little bit extra due diligence and get logs and stuff with very specific errors, let's just paste that in and modify it to suit us. I think that's a good way to go, actually. It's a reliable website. Okay, we've got that already. We only have one input attribute, so we can get rid of these. You see they've got other stuff like texturing and normal colors you can have per vertex. Oh, and it even has a handy note there. So that corresponds to the number that we gave here. So this is that input variable number 0, right? And this string here is what we called our input variable in the shader. So it can now match this up with this data here via this mechanism. So this thing describes the layout and calls that variable number 0, and we've now said that that data variable corresponds to this shader input. So you can see how it's going to feed the data into the shader now. There's a mechanism for linking those all together. So you put whatever you've called your variable, put it in there. And our shader program is going to be called this. What did I do with my create program? So I better call that first. Otherwise, it'll do horrible, incorrect things on the wrong value. So GL create program, we need to say equals. Okay, make sure you do that first before you ever use it. Okay, notice we don't need to bind this here for some reason in this part of the API. It takes a parameter, so it's wildly inconsistent everywhere. And then what we're going to do is attach our compiled vertex shader and compiled fragment shader together in this program. So this combines the stages. So I'm going to replace the name program here with my variable name. And those compiled vertex shaders, not the strings, we've already compiled those and loaded them in. We're done with the strings. Vertex shader and object. Okay, so that's attaching those to the program, and then we're going to link the program together with all the things we've attached. And that should give us a shader we can draw with. Okay, let's build and see if we got at least the function calls correct. It won't tell us if we got them in the correct order or anything. Okay, so I've made some mistakes. Line 71, apparently. Uh-oh. Warning, function GLU int differs in levels of indirection from float 9. So I've given it my array of floats when I should have been giving it the name of my vertex buffer object. Right? That was a horrible mistake to make. It's really easy to mix these things up as well. There's so many things with similar sounding names. So I should have been binding my vertex buffer object. So that's a really handy error to have gotten. I don't care so much about the const qualifiers, but let's put them in anyway to keep it happy. Great. That looks like at least the main program compiled. It does not have the ability to tell us if our shaders are valid or not yet. So that you're far more likely to make a mistake typing these things out. And that is why you should add in your error checking here later. It's easy enough to pick through your first example, but once you start adding things, it's a little tricky. Okay, so that should give us enough to draw with if that's all correct. Now what I need to do is down here where I draw, I've said we're going to use that vertex array object so we know what data we're about to draw with, but I'm also going to tell it which shader program we want to draw. So this is the what to draw. We need to tell it how to draw or the style of drawing. So it's not bind anymore. For some reason, shaders have use. So use program is the keyword. And then I believe it just takes the name of our program. You can see why there might be issues learning OpenGL with the API consistency issues and naming issues. But there you go. And I'll unbind that again just to be extra safe down the bottom. So before you're about to draw something, use a shader, bind a vertex array. If you have textures, you would also set them up there too. And then we can draw. And there is a command called glDrawArrays, but will suit the way we want to draw this. There's a lot of different drawing commands. This is the one we want. Let's go look that up. So grab draw arrays, and then let's look that up in docs.gl. Where did I put that? Okay, for OpenGL 4. And it said, okay, first we have a mode parameter. So it's asking us what primitive type we want to draw with. We've got points, various types of lines, different arrangements of triangles, strips, fans, on and on and on. You'll notice it doesn't have quads. If you look at the older APIs, they'll allow you to draw rectangles as well. That doesn't work anymore. So even if they had that option behind the scenes, it would have to split it up into triangles for you because the GPU is only able to draw triangles. This line stuff in OpenGL is terribly badly supported, so do not rely on anything from the lines. It's rastered 2D stuff, and some GPUs just don't do some of the commands they're supposed to do. Give up on that. If you need to draw lines, do it out of triangles. Seriously. Unless it's just a little play around debug thing and you don't care if it's unreliable or not. If you want to ship it to customers, do not do anything with GL lines. I wouldn't even rely on points. It's worked on every graphics device that I've used it on, but you will notice if you're careful with points, you can actually scale points up and down in 2D. This is nice for particle effects and things, but some devices will scale up a point into a circular shape, and some of them will scale them up into squares, which is super unhelpful. So don't rely on anything other than triangles, and then you have a few different ways of organizing triangles. We won't get into that. We just want basic triangles. So there we go. That's us. GL underscore triangles from mode. Okay, and then the next parameter is where to start. Start with the first one. Start with the first point, and then the number of vertex points to draw. Not the number of triangles, the number of vertex points, which is 3, because we had 3 corners of the triangle. And hopefully this will actually draw a triangle for us. Ooh, fingers crossed. There we go. So that's the first triangle. You have hello world in most programming. In graphics, you have hello triangle. So that is how you get started with OpenGL. Every other way of setting up OpenGL is easier than Visual Studio. So if you're on Mac or Linux or a GCC on Windows, you won't have as much trouble setting up all the libraries and things. But I think most students want to use Visual Studio. It's what they've got available. Maybe they have a license, they've got it in their labs. That's what they're going to use first. Or it's what people usually use, so they want to keep using that. Okay, so that is your entry to low-level 3D graphics programming. It's all fairly similar from now on. So any API will have, once you've got past the starter stuff, it's all similar. You're writing shaders, you're manipulating things in 3D space, and you can have a lot of fun. So what we could do is just to give an example of something cool you can do, if you get the time as a variable, you can start animating things, and it's really easy to modify your shaders to animate either the positions or the colors. You can do really cool things with the time and sine waves and colors. And if you want to get some nice examples of that, there is a wonderful website using WebGL called shadertoy.com. Oh, I may have broken my stream. Hopefully it's still running okay. Okay, good. So this is an awesome website. And what's actually happening here is we have a triangle or 2 triangles covering this display area, this viewport on the web page, right? And everything that's drawn into Shader Toy is done in a fragment shader. So you just have a fragment shader, and you're writing a little program to set the color of every pixel on this display area. So there is not in this scene a 3D model of a ship loaded. They have calculated the a mathematical way of generating these shapes essentially in 2D. So they may have a ray tracing thing they figured out. They may have some mathematical description of a shape. Whatever it is, this is ingenious. And there are some really amazing effects and things you can do by browsing around, get some ideas. It will list you all the code and everything. You can also make a new shader toy. And the reason I point out shader toy is because you can do the same thing in your OpenGL desktop program. So now we have essentially a fragment shader with not a triangle, but imagine 2 triangles covering the whole screen. And all we've got here is the interface to essentially the same thing as a fragment shader. It gives us some inputs to play around with. I think it gives us the coordinates on the screen. I think you can get the mouse cursor position, and I think you can get the time. And you can play around here and live edit it, and different things will pop out. So I could say, for example, fragcolor.r equals 1.0. And I think, do I need to hit play? Maybe I need to hit play. So it's changed the color for everything, actually. And what if I say So you can actually, with these vec4, vec3, you can access individual components. You don't have to set the whole thing every time by going equals vec4. You can just say my existing one dot r or dot rg to set both the red and the green channel to 1, which is kind of neat. Oh, it didn't work. Okay, please go away, Mr. Error. I can't see what you're complaining about. Uh-oh. Oh, it's not overlapping things. RG. Oh, I need to go vec2 to tell it. Assign that to both. Create a vector2 with 1 in both channels and assign that to red and green. Yeah, so it's affected the color. So you can do this kind of stuff in your desktop shader as well. If what you do if you had this in a file, you could imagine a separate external file that you load in. If you modify it and then you could either have your program watch for changes to that file on the file system or a keyboard button that whenever you press it, it reloads that file and then does this stuff again. So recreates and recompiles your shader, stores it in the same place. You can live hot reload your shaders. So you can have just type away in a text editor on the side and see what some interesting little tweaks do to the rendering in your program. And that is really, really powerful and loads of fun. So if you get this working, I highly recommend doing that so you don't have to rebuild your program every time or restart your program every time you want to try a new shader variation. It's really cool. Um, so lots of setup, but once you get there, it's really awesome. So what we could do is grab the time, and unfortunately, getting a precision useful timer that gives you like lower than seconds precision, like milliseconds or nanoseconds or whatever, the only reliable way to do that is to talk to your operating system. So C and C++ have terrible time interfaces. I think the latest C++ stuff has this standard chrono thing. It's kind of gross to use. So a nicer way to get the current time in seconds with some precision to it. Don't use time.h and the stuff from there. It will disappoint you greatly. It might look like it works for a while, and then it gets horribly out of sync. Do not rely on that. So if you're using the time, unfortunately, you have to use operating system stuff. GLFW has a wrapper for that. Um, so you can get the time as a double. So the current time in seconds, GLFW get time will give you that, right? And then you've got the time in seconds, which is great. That's all you need to do some cool effects. Um, if you combine that with a sine function and sine waves, you can do fantastic things with colors and shapes and animations. So what I'd like to do is give that time to my shader, my vertex shader, as an input. And there is a facility for doing that. We can give an input to the shader from C without having to code it into the vertex buffer and rebuild that. That would be really tedious and slow. We just want to give it one float. And we can do that by going up here and going uniform, which is the way of giving it like a constant value it can use for doing interesting stuff. And you can update that really frequently. And I'm going to say it's a float, and I'm going to go U to remind me it's a uniform, and I'm going to call it the time in seconds, right? And then we can use that, but we need to hook it up. So we need to actually send it from C to our shader. There is an OpenGL interface to get that, and I am going to say GL int the uniform time location. I'm mirroring the name I've put up there just as a reminder of what it's called, is equal to GL get uniform location. And then I think I need to give it the shader program and the name of the variable, the string for that name in the shader. And that lets me modify that time. So whenever I want to, I can now update this value. Uniforms will start with a default value of 0. So if I do this and I go, you know what, I want the y coordinate of my position to be affected by the current time. And I don't want it to just zoom off into infinity. I want it to bounce around and animate within the space of -1 to 1. What about if I go position.y equals or plus equals perhaps, so that I don't lose my triangle shape. Sine, and if you look at the quick reference card, you'll see a bunch of these math functions are built into GLSL, and you can look them up. So the sine of the current time in seconds. Okay. So if I run that now, I don't think it will do anything because it should default to a value of 0 until we update it. Fingers crossed. Okay, that's good. Usually your triangle disappears, and then you spend like 4 hours smashing the keyboard going, where the hell is my triangle? And even really experienced graphics programmers will complain that they still have this problem, 30 years later. So don't worry if that's the case. That's normal and expected behavior. That's why setting the background to a gray color is handy. If you don't see your triangle, check these fastidious little, especially this stuff here with the vertex array pointer. It's easy to get these variables in the wrong order. Um, and other than that, make sure you've set sensible positions. That's why it's handy to draw this stuff on paper, because you can see if you've set a value that's outside the range where something would be visible on the screen. If you've put like 10, 10, 10, or positive 10 for your x values, it's not going to be inside the screen. So between -1 and 1. The other thing that always happens is you've put it behind you. And if you've got we don't have a camera yet. If you had a 3D camera, when people place things, it's often not on the screen. It turns out it's behind them. And if they turn around, it moves and it's still behind them everywhere they turn. So that's a nice one to figure out. Or they're inside an object and they're looking from inside out and it's got backface culling, so they never see it. That's another tricky one to solve. Okay, so we want to update this value. There is a function to do that, and we can, after where we go, use program so that the program is bound. We can call GL uniform, so we're updating a uniform. Only one float within our uniform. It's not a vec3 or something, and it is F for a float. It's a C API, so there's no polymorphism of types. We have different function names for different arrangements of types and number of components. We give it that location that we derived. We could actually check this. If that's less than 0, it means it couldn't find this in the shader. So you could do a little assert there or something. And the value we want to give it. And I want to give it the current time. Right? There is a variation of this program called, I think, GL program uniform, and you no longer need to, you can use it wherever. It doesn't need to be within the use program scope. I'm going to put little blocks here so you can see that this is where the program is used. Whenever we call this, it's affecting the currently used program. Whenever we draw, it's going to be using that program. If we call draw after this, it wouldn't work. And actually, we have bound some stuff there too. So we could indent that again, just to be really clear that this draw arrays will use the currently bound vertex array object and the currently used shader program object, right? So that's might be a nice, using blocks is a nice way to keep track of that if you get confused on a bigger program. Obviously it looks a bit silly there. Okay, let's try it. Yay, so we have an animating triangle. So if you talk to GLFW and look at the documentation, you can find out keyboard commands. So you could use the keyboard to move your triangle around. And then you can start to get the idea, I think I'm starting to see how I might start to make a game with this that's in 3D and I can move around and stuff. So that's fairly simple, and sine waves are really easy function to use to create interesting animations and stuff in your shaders. If you wanted to, you could also use that uniform in your fragment shader. It's a constant across all your shader stages. It's a bit flaky in OpenGL, but if you use it in desktop OpenGL rather than WebGL, it should work in every stage. So you can just copy paste that whole uniform thing with the same name, and it should be available in your fragment shader as well. So I could do something like I want it to modulate the color of the green channel with another sine wave of the time in there. Right? So you can do some fancy, fancy stuff in there. So it will give you a value. So sine's going to return a value between -1 and 1, and your color range should be between 0 and 1. So some of that range is going to be not particularly helpful. When it goes all the way to 1, then we have all of our channels at 1, because we set red to 1 and blue to 1 already. So when green goes all the way up to 1, then we get white as the output. So that's what's happening there. When it goes to -1, it's not doing anything. So below 0, I think it'll fix that color behind the scenes. So if we wanted to, we could have made that an absolute value or changed the range so it's always between 0 and 1. We could make that real trippy by doing a cosine of time for the blue channel, and maybe, the red channel could be something crazy as well, like times 2.3 of the time, or sorry, yeah, let's try that. That should put it off phase. Oh, it didn't work. I think when it's black, that indicates your shader program probably didn't compile. So that's when if you'd actually set up error checking, you would go and see. But now you can see the advantage of having a gray background, right? Because black is like your failed shader state. We can still see it's there. You don't have to go hunting for a missing triangle. So I've made a mistake here somewhere. I probably missed a bracket or something. You might be able to see. I've never actually tried to do this in DirectX. I've only ever used the load function from a file thing, which is really convenient in DirectX. I presume you can do it from a string. There's probably just an alternative function to do that. And you can also pre-compile binaries for DirectX. One of the downsides to OpenGL is because you have like 6 different drivers, you can't reliably expect your shaders to compile the same way on different drivers. So with DirectX you can, because you have a fixed specification and fixed implementation as well. And there's only one. So you can pre-compile your shaders before you even distribute your game, and that's what most games do. So they won't compile the shaders on the client end. You can pre-build them, and that helps you hide the source code for them. And you get rid of that whole annoying stage that we're doing here. So you can't do that. You can do that with OpenGL, but I wouldn't rely on it. I don't know. Yeah, so I presume you can do the same setup in Direct3D too. Why did that not work? What have I done there that was stupid? I've said Tim seconds, so Tim's not here, I don't think. So I think it should be time seconds. Yeah, okay, so now I've got some fancy colors. We've got our kaleidoscope of colors. You can see how much fun this is going to get once you play around with things live. So I'm having to rebuild and rerun my program every time. Imagine if I had a text editor open on the side and I could just type away trying out different combinations of sine waves and fancy things, and you could be like, what do they call that, a VJ, a video DJ? You could have so much fun doing that. I did that on a couple of my projects. I had one project which was a game, and I gave myself the limitation that I wasn't going to use any images or textures, so everything had to be derived from a shader. And you can make some really interesting, noisy, stippled colors and animations and cool stuff like that, water, and it's great fun. Um, Tim Shady, yeah. So anyway, that is how you get started in OpenGL. From here on, your next steps, I've got a few tutorials on the web if you want to check out how to do more involved startup stuff and check for more bugs and things. You would next think about, hey, how can I load a more complex shape? How can I load a 3D model? You're going to very quickly run into a limitation. You don't have a way of representing perspective. So everything is going to be, if you squeeze it into this view area, it's going to be an orthographic perspective. It's going to look very 2D-ish and not what you really want for most things. So you would need to add in some mathematics, and usually you would use linear algebra to do that, to give yourself a 3D camera that you can move around the scene, and you're no longer constrained with your model having to fit inside -1 and 1 on every axis, right? You can have a 3D world of any dimensions. And then later, when you're ready to actually send this at the output of your shaders, you would convert that by using a camera matrix, multiply your world coordinates by your camera matrices, and then send it out. And you don't even need to look at it at that point, and it will put it within that viewing volume we've used. So that gives you the freedom to have a 3D world you can move around in. So moving towards that would be your next stage. Think about maybe making a box or something, doing more interesting animations, and then adding in a camera. A virtual camera should be your next step, and that probably means learning a bit of linear algebra. How do I build a matrix? What do the coordinate spaces look like? Yeah, so I have some resources for that online if you want to check that out. Do we have any questions? I think that's a huge amount of information for how to get started. It ended up being 2 hours rather than 1 hour, so I'm sorry I dragged on a bit, but at least I got to show the most horrible parts of how to get started with Visual Studio. I don't think I swore much at the funny little menus, maybe a little bit. Apologies if I offended anyone with my frustrations, but yeah, that's how you get started with this low-level graphic stuff. With the C programming language, it will work fine in C++ too. Thank you. I'm glad that was enjoyable or useful for people. Yeah, if there's anything else you'd like me to cover, um, certainly give me a yell. I was thinking about maybe doing a WebGL version. It's the same kind of stuff, but in a web page. That should be really easy to do. Um, in fact, it's almost exactly the same, except without the horrible library setup that took nearly an hour. Um, everything else is almost identical. Cool. Well, I'm going to take a break. In that case, I'll keep chat open for a bit in case there's any kind of follow-up questions or anything that people think of. If you try to build something and get a bit stuck, feel free to drop me a question on Twitter or wherever feels appropriate, and I'll see what I can do. Yeah, that's my main. So what I was really hoping before Vulkan came out was there were people, there were rumblings of this like GL Next, they were calling it at the time. What I was really hoping is they would fix what I saw as the biggest problem, which was the onboarding learning curve and the consistency of the API. They fixed the consistency, I believe, but it's far worse to get started. I spent a week with it and didn't get anywhere. So I think that's a real shame. I think for me, there's like a low-hanging fruit opportunity to have a powerful API that is also, and it's like something that has to happen. So I'm going to wait for the next iteration of graphics APIs to come out. And I don't think you should have to use an engine to get a nice start. I think there's a piece there that like, come on, we can do it. So maybe the next generation of graphics programmers will fix that problem. Because you've got to get people on board it. If no one's learning it, it ain't going anywhere. Okay, I'm gonna end the stream. I'll upload this to YouTube if it's useful for people later. Um, but yeah, have a good evening or wherever you are in the world.